Hello. Hello. Additive manufacturing. Sir, 1 minute speak, sir.
Thank you. I think uh, probably. Oh, okay. Yes, yes, sure.
I got
I think.
confused. Mine is all the same midnight.
Say again. Okay. Yes, yes, that's right. Do we start now or in 6 minutes, right?
Yes.
Over there is 11.
Yes.
Or we can start now. I don't know.
Yes, we can start. Now, can you please come and occupy the front rows, maybe? Comfortable there?
Oh, I think my book is disappeared. The copy I gave me.
That our students only they have reviewed.
Right. I use that for.
Oh, you want to use that book?
Yes, if possible.
Now?
Yeah.
Now. You want to parallelly want to show them that book or like one?
Yeah, and then actually I use that to prepare or change slightly the slide.
Right. So you want to put that as a
Yes, if possible. Is that
this
talking now? So I can watch the time there, right?
Yes.
11:25.
Yeah.
It's not exactly the same here, but
Maybe
I will use that one.
Yeah, you can.
Thank you. Yes, yeah, I got it. Okay. Yes. Thank you very much. Shall I start now? Yes, sure. Again, just to introduce myself, I can speak here, right? I'm Chinapat Panwiswas from Queen Mary University of London. It's a great pleasure for me to be here today, and just to share with you some thought about what is the modeling of additive manufacturing, especially for metallic system. And before that, I want to use this lecture to actually give some mutual understanding about what does it mean by additive manufacturing, 3D printing, 4D printing, what are they, what is that actually. So I just, about the outline of the first talk here is about, we need to know a little bit about history, and then you will know that the concept of 3D printing or additive manufacturing is not new anymore. It actually exists here since 1800, something like that. But the way we do it differently, to make it, to use this concept for manufacturing is actually relatively recently, about 50 years. And then after that, we will look into what is a different in terms of after industrial revolution, what is a different from the traditional manufacturing processes, and then what is the market and opportunity, that we have, and as well some challenges. So this lecture tended to be kind of rationales or some fundamental understanding of additive. So I just look at, this is actually released just today morning at time of India. And then I have seen Indian UK government program that want to have a collaborative project. What I can learn, actually, don't look at anything, just the figure here. You will see that that means the future. We are talking about the future, right? Future is about green, is about solar panel here, is about wind turbine here. And this actually create an opportunity for, it's not just UK and India, but it's actually global opportunity that we can looking forward. One of the argument of additive is that word investing, because it's quite energy intensive process. But sometimes if we understand the process very well, that is the objective of the course here. I believe additive is one of sustainable manufacturing processes that we can actually leverage the knowledge from science in order to technology take up. And I would like to start with something, future. So this is the future that people thinking of. I just borrowed this video from Siemens company.
Delivering virtual representations of real-world products, systems, and users. For example, the digital twin of an electric motor not only showcases form, but also analyzes functions, from the rotation of the shaft to thermal conductivity to data from sensors and beyond. What's more, the digital twin continuously evolves, thanks to the flow of data, user experience feedback, and new inputs, and it's greatly impacting development, production, and operations. In development, a product's behavior can be simulated and tested long before a physical prototype has been built. Siemens utilized the digital twin to develop a world record-setting electric aircraft motor that not only weighs
You will see from CAD model to actually numerical simulation, and then going to the digital twin, that engineering-based simulation things. And again, this is a kind of design of manufacturing. This is 3D printed part.
the result, a truly unique panel shape and configuration.
Again, this involves simulation again, the CFD,
Previously designed.
Star CCM Plus here for computational fluid dynamics. And this is robotic, robot-assisted manufacturing process. Again, this is subtractive manufacturing process that you can learn here.
The forces that push the robot away from the milling pad can be calculated and compensated in real time, keeping the robot in its path. When it comes to operation, digital twin can compare the sensor data of a real point in real time with the simulation of its point. The availability of the point parallel to operation can be reliably predicted, and sudden disruptions become a thing of the past. But this is just the beginning. And
This is just the beginning.
the future.
And
Merging digital twins with artificial intelligence allows computers to independently
And then you will see previously the composition that they have titanium or whatsoever.
with California
So just want to,
aims to build customized sports cars.
this is automotive application.
In operation, the digital twin breaks with traditional paradigms and opens up extraordinary possibilities. That's why digital twins are the innovation backbone of the future. Siemens, ingenuity for life.
Yes, and actually this is about digital twin. It means different from different people, but in order to go to that future technology, the digital twin of those fancy component, we need to understand what happened in the material scale. And what I'm going to say today is about how to link material and the process together. And that is the next slide. So the outline of today's talk is about material manufacturing. So manufacturing is not just manufacturing. It's need to know about material as well, because additive is a it's a process sensitive, how to say, manufacturing. That means you need to understand what's happening during additive or manufacturing of metal. What is actually people do in the past, and then we will learn from that as well. And then some concept from material and metallurgy perspective. How can we actually print all the jet engine, for example? That is the question that people are trying to achieve. Some of them show already in a small scale jet engine. They print them all using additive 3D printing. And then basically the concept or the talk in the next few days will focus on powder-based fusion process. This is one of the 7 additive manufacturing families that are following the ISO standard that I was going to talk to you. What is the fundamental of that? Why is so concerned? Why is so interesting as well? So paper published in Science and Nature talking about closing the gap of 3D printing with the material, for example, that you may see in the recent year. And then what is the perspective for me that set the scene for the next few years about data-driven modeling for additive manufacturing? And then I will summarize the first talk, introductory talk later. So what is the material manufacturing actually? So when you say about material and manufacturing, it seems to be something related, but normally people seem to neglect both of them each other. For example, it's evidenced by the department. They will have department of material and probably manufacturing or for example, or even mechanical. I think it is important to not to separate them, but to study this, what does it mean about material science? Is actually study the relationship between composition, process, structure, rising from the processing that you do, and then subsequent porosity and the performance. And this will understand this to improve and minimize or unlock the potential of the material that you use to give the maximum or full potential for that. And then normally we will use different processing technique or methodology for different material. 3D printing is one of them, using across not only metal, ceramic, polymer, composite as well. So it gives flexibility of the design and also opportunity. But again, to make it first right time usage, we may need to understand the process more, and this is about the course today. So for example, I said to print the whole jet engine, this is the dream. So this is a powder-based fusion process when you have the powder here, and then you use the wiper here to spread the powder, and use a laser to fuse the powder layer by layer until you get a 3D structure. I think this concept don't need to explain a lot, but why is actually 3D printing? If you look at the inspiration from the industrial revolution concept, that the first ever, is around a pre-Victorian age. You know that people knowing about how to make iron or steel systematically, but even prehistoric time is a lot known already. And then when the first introduction of electricity came at the, toward, beginning of 19th century here, refrigerator and mass production come, and this is where the new ways of producing things. I think I just want to emphasize this, and then when we have another third wave of this one, when we have the new ways of this by electronics and automation process, a little bit robot coming in now to change the way we manufacture things or we making things. And after that, just very recently, artificial intelligence, nanotechnology, including material science and 3D printing, play a role to revolutionize the way we're making things as well. So from just electronic or automotive, we make something better rather than waste a lot of materials by about 90%. I will talk to you more later. And now we know how to make better or make the, calculation faster by quantum computing, for example, that you see. And this will be vision into the 2030 onward, from my opinion, or even starting now, Industrial 5.0. I don't want to talk anymore about 4.0 because we need to look ahead when we have two important words, which is sustainable and human-centric. That means the interaction of human and also sustainability is an important factor for AI and then data-driven model or data science in the future that we use to making things better. And this is the picture why 3D printing gives the opportunity that projecting ahead to that direction. And what and how can we go into that? I mean, just a few slides, probably boring, but just is about setting the scene that this sustainability aspect actually contribute to the sustainable development goal here, number 9, industry, innovation, and infrastructure, and also the responsible consumption and the production. This one align very well with mutual goal target for the world to moving forward. And having said that, it's not only this one. I give an example from other country in Eastern country as well, Japan. They define 3D printing is one of emerging technology that we need to create for Industry 4.0. But even they introduce a new policy for 5.0 already. And this can create a social and global impact in such a way that we manufacturing things. That is the importance of 3D printing. But the next step, when we realize this actually quite important of this, how can we make it? And then we need to step back a little bit to see what we have now. So for example, if you are looking at the 3D printed of the jet engine that I mentioned earlier, I would need to emphasize that this is the high value added part that some of you may do research in aerospace material. That your concern is about, for example, you may not be able to replace this investment cast turbine blade at the moment because it's actually, the strength is not compromised using 3D printed, but there's some way using electron beam melting that you can actually fabricate it in a single crystal. Again, a lot of research going on to make that happen. Or if we try to print this jet engine, you may need to think about other components. For example, the first pieces of the 3D printed part are flying in the air in 2012 by, what is the company, a GE? Yeah, it's actually a fuel nozzle that I will give you some introduction later. So in this one, that means we need to understand not only the engineering requirement, but also we want to know to place the material in the right place in order to make it, robust and then manufacturing it in such an efficient way. So this one, we hope that 3D printing can revolutionize or change the way we make the jet engine. But just keep it in mind, and my question to this is that how we print it. And we print it without defect, because if it actually contains some defect, you're not going to find defected bread to carry 300 life. Is not good, right? So we need to make sure that in terms of material science, metallurgy, and also processing, that around this to make it more regulated or standardized this one. So as I said, existing, people talking about 3D printing, but you will see this is slide borrowed from NASA, right? Talking about, okay, you get a lot of defects, especially when you print a big part, and this is why we need to know and warn you that it's not that easy, just not like print polymer resin or some other component, but printing metal is something challenging and something that we need to take care of from scientific perspective. So if we looking at, as I said, metal or metallic 3D printing, I said before, so you will know that every time we discover or we actually knows how to make things, and probably at the very early stage, Indian has done very well with the casting or steel making, as you know, you have a company on that. And then what I'm going to say is that every time a new era comes, the age of, let's say, Stone Age, bronze, iron, or steel, and then superalloy, which is the high performance or heat reseated material here, you will see that they will have different, important or requirement for different smart or advanced material. And then now this is the birth of, you may heard about high entropy alloys, but again, this is just the way we want to map all the material, spectrum in this one chart. So the future is going to be something like a lighter, stronger, or weight, strength to weight ratio, which is reduce the weight, but also keep the strength, and how can we make it? So Professor Kumar may talk about design of experiment for metamaterial structure or lattice structure later. Again, when we understand, we want to understand this. Why? Because when you print titanium and print nickel or print shape memory alloy, it's probably totally different story. So we need to understand material science first as well as the processing of it. So this needs to come into package. So, and then this is a summarize of one example actually, superalloy. Are there anyone here knows about superalloy? High temperature material, heat resistant, high resistant in degradation, right? Like creep, fatigue, blah, blah, blah. So superalloy is one of the, I would say, the most clever materials on Earth. It's about 80 years old now, since its inception in about 1940s by investment casting. But again, the graph here show that when you introduce a new process like directional solidification, single crystal casting, or powder metallurgy, you usually introduce a new composition or new material to actually optimize for that process. So it means that, this is actually as an example, like casting. This is likely to be first generation superalloy that optimize for casting, which is MAR 200. And then you have directional solidification, which is actually polycrystalline structure, CM247LC, but there are people trying to print CM247. I would say, what is the problem? And then single crystal, this is the CMSX4, which is second generation superalloy. And again, each composition here optimized for the process, and that's work, actually. Even people trying to replace CMSX4 with high entropy alloy, but when you consider all the factors, it's not really happening yet, because it doesn't worth investing in the new composition which doesn't have superior combination of the property like existing material. But my question to this slide is that when you have new process like additive, which is actually not new, but introduction of additive to the metric printing around mid-1990s or about 2000 millennium year. So it's actually, the question is that, can we use the existing material, not only superalloy, existing material using the new process? The answer I will show you later is probably slightly no. That's because of when you decide the composition for each process, you think about a different criteria, or if you like, you engineer it differently. So that's why we need to both understand metallurgy or material science and then processing science of it. And then before we go into the process, I want to give you some, inspiration about 3D printing, about the process we call additive manufacturing. What is that? And then if you take the definition from the ISO ASTM 5290 here, you say that the process of joining material to make part or object from 3D model using layer by layer, as opposed to subtractive or formative methodology. So I will give you some example later what does mean by subtractive or formative technology. And actually, as I said before, additive manufacturing has a 7 process family or category that listed here. So apart from that, it's actually fall into all these 7. Believe me, everything is all. You have a lot of, abbreviation, but it will fall into these 7 category. So by the jetting, I'm not mentioning much, but for example, desktop metal provide the opportunity to to basically you deposit your binder onto the metal powder bed, and then you create a green part, and then you sinter later. So direct energy deposition is actually used a lot now, or one of them is a WAM or wire arc additive manufacturing, that you use a wire and then melt it layer by layer. For example, to repair a turbine blade or wind turbine, for example. Metal extrusion is actually similar, but not the same. It's similar to the, what this is called, in sintering, we have the, in certain, I forgot, but it's actually similar to MIM process, metal injection molding. But that one, actually, you have a mold, but metal extrusion, you don't have a mold, you just extrude your material when you combine your binder and your material together. This can be used for metal as well. Metal jetting is actually you deposit liquid metal, for example, if it's metal, or you deposit some material and then created the 3D structure. Powder-based fusion is something we're going to talk a lot. Previously called selective laser melting, but the standard now, even in the publication, we no longer use selective laser melting. Additive Manufacturing Journal will be rejected based upon that, because you don't know, it's now have to call powder-based fusion. But sheet lamination is also another process. It's not very popular research area, but there's something there. And then actually this is wet photopolymerization, or you use a stereolithography that people use a kind of light to fabricate the lace in the liquid bath, something like that. I will show you something. This is probably for bioprinting mainly. But the thing just want to say is that this is the things. Additive actually happened, the concept, I would say, since 1860 in the photo sculpture here. This is a prehistory of this kind of idea or thought. And then the milestone, the first patent filed on the 1868. Believe me or not, this is actually about 50, 60 years, or more than 60 years now, since the inception of the first additive machine ever that you have. And then they commercialized is about 40 years ago, nearly, 1987. It's not new technology, but the way you make this one innovate, the way you make the material in the jet engine is probably new. And then you have the first metal printer prototype in 1994. It's just P-Millennium. And then the first is on fly, which is by GE in I would say around 2012 or 2013, but around that. So this is entering the modern additive manufacturing, which we are talking now. So he's quite important guy as well. This is, I think you know EOS company by Germany, right? Or US, I can't remember. I'm not experimental guy, but he's the one who looking at the very first model of the EOS machine back in about this period of time, about 30, 40 years ago. So the prehistory of the photo sculpture, I mean, I'm talking about here, and this is because, I mean, we're looking at the US pattern back in 1864. Actually, you have something like this, that you try to basically add material bit by bit. That time is not layer by layer yet. But this is a concept of additive. You not actually machine something out, but you add something in to create some structure. And this is we call this a prehistory time of additive. And later in the topography, you will see in about 1925, you actually has the way to manufacture this contour map. So the way you do this, you actually add layer by layer. Like this is kind of Lego pieces that you build a kind of mountain or whatsoever you can imagine structure here. And this one is likely looking like additive. You add layer by layer, and then you create some 3D structure here. But the mesh size here, or the pixel that you deposit, is quite coarse in this sense. But let's imagine this is just 1925. And this is the next one is a patent on the, material deposition, actually filed to make new decorative article here in 1925. Sorry. And after that, in early stereolithography, the first ever, patent that to build a two-laser system, now we use laser to build a 3D construction of photosensitive polymer. Okay, it's actually start in the material polymer. So this process optimized for polymer. That is the message. And then this is the method that, and then along with the apparatus scheme or drawing that show how to make this construction, this production for this polymer using two laser here. Again, this is the patent granted in 1927. So I will base the date on this documented evidence here. So that means this is probably can say very early stage of, modern additive manufacturing machine or manufacturer. So next one is about one Japanese guy called Dr. Kodama that actually proposed something on the new 3D printing. Again, it's based on the idea of stereolithography, coincidentally. And then he needs to actually withdraw his application for patent because of funding issue, something like that. Because as you know, to apply for US patent is actually a lot of money, is our investment, right? To let the world recognize. But after that, there's some people actually look after, which is actually Chuck Hall here, just find the patent. And please remember the name Chuck Hall is the very first one who actually commercialized this and then probably billionaire now. So in 1984, it's not too far from here, it's exactly about 40 years, right? 1984. So this is the first origin of the manufacturing of the 3D printing in metal now. So I probably think that the same concept applied to the Professor Kumar lab as well. I visited yesterday. So this is Charles Hall here in front of his first commercialized available AM machine in 1987. And this actually, someone said to me, is that going to be a very expensive process. If you talk about additive manufacturing or 3D printing for some high value added part, it's not going to, you're not going to waste your money to print something doesn't actually have some, how to say, value, right? Because additive is for a niche application, like implant, like something that, not construction for sure. We were not going to print metal for construction. But if you look at, for example, in automotive area, like in the motorsport, for example, or luxurious car, you see that the designing of the car actually more expensive, twice expensive than the manufacturing cost itself. So they suggest that actually manufacturing, when people say that additive is so expensive process, it's probably not true in some areas. So the answer to some of my previous colleague question is that we need to select the correct application for metal 3D printing. We're not going to print metal for everything, but it's actually some area which require kind of delicate care for that, like blade, in aerospace, some automotive part. So that means engineer, material science, and mechanical engineer or computer science need to be involved to move this field forward. So I would like to give some review of the method, give you some context about different modern 3D printing technology. So the first one is, the first one is stereolithography or SLA. I believe you know, or every lab, probably in your lab here you have this as well. It's small and an affordable machine that every university can have it for students to have a project with. So this is just a light, and then you have a resin, put it there, probably heated substrate, and then you basically have a liquid bath here as well later. So this is affordable kind of machine that may be useful as well for bioprinting. This machine can be adapted to use for kind of tissue or kind of this kind of printing as well. But this is some research need to be going on. Again, that's what I said previously. Need to select the material along with the process that we're going to do. So in this case, it's probably not for metal. But anyway, that's just to review, and this is called wire-based additive manufacturing. When you deposit the material, this is the laser nozzle, right? And then you use arc wire, this is wire arc additive. So you add it layer by layer until you get the 3D structure here. So this one we call near net shape manufacturing as well, because you don't need to do anything much after that. But it is a slow motion of these things. But you will see they will still have a problem. You see a balling effect or surface roughness here and a melt pool whatsoever. But this is something to concern next lecture. Don't need to talk about now. But you see layer by layer here it's like making a cake. We call cake, right? You add layer by layer, and then you get the pieces of cake here. And that's an example. The next example is actually powder-based fusion. This is something we're going to focus on in the next few days. And then you have a chamber here. You have the powder feedstock here. You spread the powder onto the substrate. Whatsoever how many substrate you have. And then you swipe it another direction, and then go into this used powder. And you use laser to fuse them layer by layer until you create a 3D structure. In this case, I think it's probably a turbocharger for automotive. Again, this is a delicate part that usually you use about 40 manufacturing steps to manufacture, but you reduce it to one without waste. That is the key idea. But the things that control the quality of this part is actually the laser matter interaction, which we are going to focus in the next lecture later today. You see now a lot of spatter and everything coming out. And this one, when you remove with care, and then you will get the part 3D printed. Again, the health and safety issue here is probably delicate, and it's expensive process. That's why I said we're not going to print this one for microphone, for example. It's too expensive. But if you want to do it on purpose, probably yes. We need to be careful about that. And then you get this part, and then you will notice that this video very good. Actually, you can see that there's a surface roughness and support structure associated with that. Again, this requires a lot of not only metallurgy but also engineering, mechanical design of experiment to allow this happen. So if we summarize in a very quick short for this one, you get the pro of this process. Actually, you get a near net shape of complex geometry. That is why you use this process. And then you can do rapid prototyping on this one. You get, if it doesn't do something wrong, it's actually, we expect it to get less scrap and waste when you know the condition well, how to do this. And then the con or the disadvantage of this process, actually, the feedstock at the moment is still expensive. If you talk about high quality feedstock, especially for biomedical implant or medical grade implant powder, it will be expensive, titanium, for example. And then defect rate is still high, but this is the way why research is important to reduce that once we understand the interaction of this in the material. And then resource stress is actually another issue, people looking at that from the composition of material, processing, structure, and property perspective. This one is become issue, but now a lot of research going on trying to make it possible. Like for the material structure that you can design a lot of property out of the range of the bulk property. That is the concept that is not possible using only CNC approach, that you cannot get the internal structure in a micrometer length scale, something like that. So that's why application of this is so related to the process you are going to use. Next one is actually to recap. That is additive manufacturing, but now we are going to talk about how can we replace those traditional process, or even we cannot replace, is to understand what is the traditional process for metal manufacturing. So we have forming, casting, joining, and machining. I would like to make some big difference of joining and additive manufacturing. Joining, you don't need to add material sometimes. If you don't use filler material, you just use some power source and then fuse them together. We call joining. The difference of joining and additive is that additive is add material and join them together. So that means, in my definition, welding and additive are different. But people may say it's the same. But anyway, I will show you why different later. In the probably by lecture 8, you will understand why I make it different. So this is forming process, and this is a big forge hot ingot machine here. You will see, probably you sit in the steel manufacturing plant, and then after that you punch this. I mean, I believe mechanical engineering also need to learn about manufacturing process like this, right? You upset of this one, you get some skin of this manufacturing, you punch it, you force it. And then the way you force it, and the temperature and whatsoever, and then you drill the hole to do the ring rolling later. So in a very hot state, you drill the hole, do ring rolling later. You will see that this is do with care. And this process has been done long time ago. It's not just new process at all. A robotic or robot-assisted additive that you talk is actually use something already exists to do things here. And after that, you roll it. I mean, this one I want to say later that this link to the microstructure development. The way they do is actually make the near uniform grain size in order to get the property across the section uniformly. Otherwise, if there is some weak area, you won't be able to, make it fly. For example, if this one is a disc, or this one is the ring for engine, for example. And that is the thing. So, and later in the probably next lecture or the lecture after next, you will see how we simulate this process to get the correct stress, thermal and stress field in order to get or optimize the process to get better understanding when you want to change the material. Let's say from steel to titanium for jet engine component, for example. And this is the thing. So if I summarize this, we call this is a subtractive manufacturing process. You will say that because it's subtract, or they actually you waste a lot of money. Money and also material as well, environment as well. Microstructure supposed to be uniform. That means it's quite robust process that's used in the quite high value added manufacturing company. And then the mechanical property, I mean, given that the structure and property are strongly related. So if you get the grain size, according to Hall page relation, you may get the similar strength across the section, something. That is the ideal, but in reality, things like that need to be optimized. But anyway, that is leave it for another matter. It's not additive. This is just to make the difference. Large production is actually correct because you can do in the bigger scale, not like additive that you can now only doing it in small scale. But again, it's about the application that I said. The disadvantage is actually this equipment, the toolings are expensive. It's only big company can afford it. It's not possible for SME or smaller company to do this. And process difficulty is actually another problem because you need to use a robot algorithm to program it from the final shape. It's actually relatively simple, but actually hide it in the value. You need to have the kind of structural integrity for this part, so you want to control it in a robust manner. So this way you will use forming. I mean, forming, I will have another diagram to summarize this. Forming, that's one of the, forging is one of the forming process. And then you know, you waste about 90% of the raw material in this part. You get only 10% in the final product. And this is not sustainable. This is one of the subtractive manufacturing process. I did comment as well in my NatureCom commentary back in 2020. So next one is casting. So that means you use some heat source to heat up the metal, and then you pour it. In this case, in this case, it's actually aluminum alloy, and this one actually is sand casting, I believe. And then this is uses for automotive part. I mean, complicated, and then surface finish is good. You say this is a liquid aluminum here. And after that, you will see how things solidify, and you see some shrinkage later as well. Yeah, it's level up here. Stop. And then they start to solidify and shrink a little bit to the central here. And later, later you will remove this part. I mean, again, robot is used for this kind of purpose. And then you get quite complicated geometry for this process. And then you see this is automotive part here. Again, again, this is ideal. This process is ideal for complex geometry, good surface finish usually. And then the con of this one, or disadvantage, is actually equipment is so expensive. And you probably some way, somehow, you compromise the mechanical property. Again, if you notice from this, that means previous process may related more on the solid mechanics part, and this one is actually more fluid. So because you have the fluid, actually liquid metal as a fluid, and flow into the mold. So please keep this in mind that I will use this later. And next is actually joining. We as I said, welding. This is a torch welding in this case. So you weld it. I mean, you have some probably material here, and then you melt it or in a specific location, and then you join them together. Or you use something called or you use something called and this is the structure that you will see after that process. And then sometimes you don't need to have any material to join them together. You just use a frictional force, I mean linear friction actually, or rotational welding, friction welding. So you rotate the material very high frequency until this to create a kind of joining area, not to melt ideally, but actually these two pieces will join together. And that is the things we call welding integrity that you want. The weld, which is the weakest area, due to the microstructure in the joining part, are different from the parent and the heat affected zone. So this one, the phase transformation kicks in now. So the base material, heat affected zone and welded zone have different microstructure, which subject to different property. And then you may get the weakest zone in this area. And this may be an issue if you don't actually manufacture with care. That is to summarize, this one using for probably repair or rejuvenation of the material. And then mechanical integrity is important. You can use this for these similar material like steel and nickel, for example. And then for the advantage of this, you may create some residual stress, especially in this zone. And this is the weakest area. Actually, need to be actually take care of this area. The local microstructure, I mean, in the weldment zone is changed. So you need to look after this very carefully in order to get the property right. And then fatigue and distortion of dynamic loading will be important if you doesn't make this right. And this will be the failure area for the, let's say, flying engine, for example. Last but not least is the machining. It's actually not very, I think it's inclusive. So I think you know a lot if you're familiar with 3D printing. I mean, machining is kind of CNC kind of approach that we use the machine here to remove the material, to get the shape that you want. Again, the remaining material that you want is probably only 5 to 10% from the first raw material you use. So this is not sustainable, but we use this for long time. But the way to make it sustainable, probably dealing with a scrap or swap material that you're going to use for future application, for example. But again, this is machining, traditional, typical, every country has it. And just summarize, the surface control of this is very good. And then you get a net shape on very net shape because that's what you want, like a screw knot or whatsoever. And this is a destructive, not subtractive, but not, it's destructive and subtractive. That means you destroy material and then you remove it. And this is, as I said, most of the product require this kind of precision. Some company call precision manufacturing, but again, this is not very new manufacturing process. But yeah, anyway, just to make you aware of this. But if you compare additive with traditional manufacturing process in terms of economics, you will see that the cost per unit pieces for traditional is actually, if you do very small quantity, it's so expensive. But if you do kind of mass production, the cost per unit pieces is actually very low. And this is preferable for company, right? But additive, actually, this cost per quantity is not very much different. So it's kind of very straight line. So even you make one or make 1,000, it's relatively the same. But again, the way you make it without waste, this is important. It's not just making it. It's about whether or not you have a robust approach to do it correctly. There's a big even point here. So this is not going to work for traditional process, for example. You're not going to make mold like this complicated shape. You may need to use another approach. So the new design of this, with the new design and the additive process, you may be able to shift this one to the right, but again, it's not comparable with the, I mean, you shift the back even point here, but anyway, additive still better. So if you compare about the cost with the complexity, if you have a very small complexity, your cost is not a lot. But if your part is so complex, that means traditional process like you use CNC or machining is so expensive. But additive is relatively in different direction of this cost per quantity. When you have more complexity, the cost will be slightly increased. It's not massive. Again, we may need to design with care on the design of manufacture or do some analysis on thermal management on this part in order to get with the minimum stress distortion, for example. And this is perfect for using this kind of process for metamaterial design. And this metamaterial, which is the future of manufacturing, that actually the idea of this is actually you want to produce a new property that far away from bulk property. Example, very good nice research from Professor Gruma lab, having a titanium. The bulk property, probably you have elastic modulus about 100 gigapascal, but with metamaterial structure, you can lower the stiffness by 2 orders of magnitude. You can achieve about 1 gigapascal on purpose when you do correct design of experiment. So I believe you will hear more from him later today or tomorrow whatsoever. But again, we also use this one during very difficult time in the past 3-4 years in COVID. So the goggle here, we printed by additive, so fit for different, people around the world. So for example, in Asian country and European country, you may not be able to have one size fit all. So that means this may be useful to print this one. And then definitely this kind of 3D printing concept had been used in the production line assembly already. And then again, for this one, you don't need to take care much. Even it's important for life, but it's not flying component, right? You can use, there has a knowledge barrier, and it's timely for this pandemic in about 3, 4, 5 years ago. And then the con of this one is cost effective that time. It's still now, but we need to find new business model to make it effective. And then the production rate is very slow. Even we can actually use this fusion metal additive to produce this part, but still relatively slow with a conventional process. But by the way, we get more personalized, and also this is the future. Sustainable, personalized, and all these things. And if you look at in terms of the market or economy, the patent actually filed, from additive since what I said, the first manufacture the machine in about 1997, 1980 something, you see is increasing actually in terms of the patent from about 50 to now. Now it's more than this. It's actually shooting up to about 1,000 now. So your cumulative of this is a lot of patent actually in the AM industry. So in short, additive manufacturing industry. But the application submitted is far more, 3 times more than there's something accepted or issued. Anyway, it's still an opportunity. So in terms of product, you will see that they anticipated growth. Again, this slide is relatively old in 2019. So it's growing in 2018 by 33%, 1/3 of the sector. It's quite a lot, and this is in the service and product. The product is in blue. You will see that more and more AM part is actually receive some attention or realized by industry. And that's this opportunity that Professor Kumar mentioned earlier today, that we may anticipate about 80 billion market for additive in 2028, right? So, this beyond the graph by 10 years. So, again, now is more about what is the AM or additive manufacturing in metal, its application. In automotive, aerospace, and tooling, this is some example in automotive. BMW, has been used this for printed some wheel. Again, this is a luxurious car, so you do it on purpose somehow, but some part like a turbocharger, they use 3D printed now, a lot of research. I think I can say that I evident that 10 years ago that they have a big automotive company approach to us in Oxford that time to research on the automotive part for 3D printing. But having said that, you see automotive part, you have a lot of part that's now been 3D printed. So it's not just speculation now, it's real, it's happened. And this is the first the full nozzle for jet engine. Again, this is fired by GE. So this is the steel, I think. And then in terms of tooling or something complicated, you can design using additive here as well. So more than that, you also have some application in biomedical implant. I think we will hear more from Professor Kumar from a case study or application. And then you also have some game avatar or something like that. This is a big market as well for entertaining or whatsoever, as well as the jewelry. It's a lot of patent file in this area. Especially, I would like to share with you some colleagues in UK did file patent to fabricate platinum, actually successfully using some nanoparticle. So this is something still going on. The research is a lot that we need to do more. Again, that is jewelry. So that means small amount, delicate part. Again, that is the application. Or this is the architecture or display, which is actually you never ever before you have to do it by hand, piece by piece, but now you can print it. And this one will be useful not only for museum display or architecture, but it may be a prototyping for assisting a medical doctor for the learning or studying in a very complicated channel. If you use the X-ray 3D scan and then you print it at some sensitive location, this 3D printing proof is useful for education as well. So it's a numerous opportunity for 3D printing from design, as I said, ultra delicate component or geometry, rapid prototyping, you also shorten the design cycle as well. And also you actually, you don't need an unnecessary assembly if you want. If you see here, this is a bone, let's say if someone has an accident, has a bone fracture, and you want to print something that has the bone match with the cancellous bone with the low stiffness using titanium. Now, probably it's possible, but it's still in the lab, not in the commercialization. But it has an opportunity that we can design mixed with material science, metallurgy, and processing to make this happen for the near future. And then the manufacturing economy is actually free from large-scale equipment. And then you don't need a large-scale equipment to fabricate this. As, for example, you may invest probably $250,000. It has to be that scale, unfortunately. It's still no cheaper than that for the decent, for research and for high manufacturing part, or probably up to $1 million with the full option machine, but you can do more than you can anticipate it. Yeah, and then no less machining or tooling or waste. And then this production time is actually reduced if you know process condition well, what is the right process. So the business model for the next additive manufacturing industry is that it's not just sell the the machine itself, but it has to come with package saying you have a material A, which is titanium, and you need to come with a processing window or processing route that to make it work for some application. So now, from now onward, the business model will be like that. So they will sell with a precise window for you to choose, but impossible because sometimes for the company intellectual property, it's impossible for you to review that for them that I want to do this in the future. So that's why we need to have some knowledge, if it's not in mass production yet. So during the intellectual property or secure process, so you may need some material engineer, computer science, physics, chemistry, blah, blah, blah. But anyway, this is still opportunity. So we use this as well for the repair and overhaul in transportation. But also in aerospace, it's more and more. I have a project with the aerospace company looking at using the wire-based additive to repair some turbine blade part, for example. So this is coming. And in space manufacturing, that you may see the program from NASA that they try to print something in space. It's also possible now as well. There's an experiment going on in this area. If I remember correctly, led by Purdue University or Carnegie Mellon, for example. And then you have the material property. You can actually tailor it as much as you can. This is all about my research. So if you understand the interaction of material and the heat source, you may be able to tweak or fine-tune the material locally. So the ideal cases is that you can do like fine structure here, coarse structure there, or something mixture over there. Because the different part require different property when you design it. But with traditional process like forging, you'll not be able to do that easily. But additive provide you opportunity to do that. Or you will have some material structure for additive, because the signature of this process actually rapid solidification. So we may use of this to leverage the use of this one for specific application like in electronic structure, for example. Electronic devices, not structure, yeah. And then you can do even graded material or someone called functionally graded material. That means you have slightly copper there, more steel here, and then slightly or graded, like that you will have a shredding of the material, which is not possible before without additive manufacturing, right? So this is an opportunity, but still there's a challenge that we need to overcome to get this opportunity possible in the long run. Let's say this is the disk. The idea is that we don't want to have non-uniformity in this disk. We want the disk here has a single kind of grain size throughout, which is not possible traditionally. But we hope additive can offer this opportunity to manufacture that. So this is the challenge. Having said that, I just want to, probably that is the very first part of the presentation. And next is actually how can we summarize all that in the context of material and manufacturing processes. So from this one, I just want to show that the way you print jet engine component or the way you print some stand for your material, for biomedical, is actually physics is the same, but the way you implement it are so different. So you need to take care of, even you are dealing with titanium, let's say they're both titanium blade, and then the titanium 6O, they use both the same material, different grade anyway, but we can transfer the knowledge of the physics that going on, but in terms of the property, for medical, you may concern another factor on non-toxicity or bioactivity. But for aerospace, you concern more about structural integrity, or blah, blah, blah. Again, that's what I want to say. We need to, when we say something printing titanium, it's not just titanium material that we're talking about. We need to say, along with that, we need to talk to yourself that is what is the application you are looking for. And now, we're going to summarize what I just said in the probably 70% of the talk this lecture. So we have in the category of the metal 3D printing or metal additive manufacturing processes, we have powder-based fusion, which is one of the standard. We have direct energy deposition. We have solid-state formation like lamination, sheet lamination. So the feedstock associated with that, definitely this is powder. The feedstock will be powder for sure. And then you may use different process to process this powder using the heat source of laser heat source or electron beam heat source. Again, they are so different in detail as well as in the physics, the way they melt as well. So this will be talking a bit later. Direct energy deposition. If you talk about powder feedstock, it can be a kind of array of powder deposit onto the substrate. This process known as a bronze powder process or deposition. And if you talk about wire, there's few options you can choose. I would say arc-based deposition or laser wire, electron beam deposition. Again, this depends on the heat source you use for that. Again, there's some detailed difference in different manufacturing process for different material. And then last but not least, the solid state. So you may use ultrasonic additive for foil here. Not much research from my side, or friction stir additive. I have some research on this. Or if you combine this and this, for example, this we call hybrid manufacturing. Again, this is leave it for the later matter. And then they still have other additive process like I mentioned, especially metal, they can use bi-jetting as well, material extrusion, jewel printing or material jetting, or even wet or liquid bath is possible. Again, we're not talking about that for the moment. We're just focusing on probably first two sections. I call this process like melting-based additive manufacturing. So you need to make it melt, make it liquid first, and then you join them together. And then how to choose this one is depend on different factor. I mean, from engineer, I borrow from NASA slide here. Depend on the cost, material property, internal geometry, availability, scale of hardware, complexity of feature. And this deposition rate and then the precision of the feature are also big consideration. Why people still using powder bed? Because they give at the moment the highest resolution for metal 3D printing. The resolution is the same as the powder that you use. The finer, the smaller resolution you can achieve. For example, now there is a new term called micro LPBF. That means you print something in the micro scale, sub-micron powder length scale for some electronic or some delicate part purpose, or even printing some notebook things. Again, for the arc-based deposition, the characteristic length scale is larger because the melt pool of that size is actually around millimeter scale. So you're talking about large component. but still you need to think about residual stress development or thermal management is key. So again, that we will go to in the different process and the science behind that later. So this is in terms of process, AM process. And then as I said at the beginning, we need to talk in additive manufacturing or AM, not only the processes, we need to talk about as well the material. So this is a summary of the material used so far, but not very inclusive, not fully inclusive in AM. When I say AM means the LPBF, using laser, LPBF, using electron beam, and then direct energy deposition. So you will see this is all metal AM. So from nickel, again, this is not inclusive, but you will see this one they prefer in US because they use for the NIST or National Institute of Science Technology a lot. This is for space application. Try to print this one, but proved to be quite okay. It's printable. Anyway, we talk about this later, and also Wasperoid. I mean, copper is also used or print a lot in the heat exchanger application. Aluminum base, again, as well, try to print some complicated part, but still aluminum is very high refractory material. That means we need to manage it very well. I mean, and then iron is a lot to print. For example, 7.4 pH. I think your lab also print as well 7.4 pH or 316 standard. And here, and then the titanium base. I mean, people trying to print Ti-64, titanium 64 or gamma titanium alumini. Again, trying to replace the superalloy, but I don't think it's not successful yet, or even some program already closed down because of the metallurgical defect or understanding about cracking. Again, cobalt based, you say cobalt chrome is also biomedical application as well. Refractory is attract more attention at the moment. It's hard to print material high temperature, high melting point material here, using for space nuclear application like tungsten, moly, tantalum. Tantalum also is my research is here for biomedical as well, tantalum printing, and also C103 actually is a new NASA program for niobium-based alloy for space application. Again, they use refractory, and then they have a biomaterial. As I said, you can print whatever you like. I mean, the lecture later, I will say one technique we call in situ alloying. We mix something using laser together. So we alloy them during printing. Yeah, and then you can do bimetallic. And also you have some metal-metallic composite. It's a lot actually. Very first paper in high strength aluminum alloy, they try to print it. Paper by Professor Teresa Pollock from UCSD, Santa Barbara. Also, again, this is the same concept as a casting they use in corneland or particle to break down the microstructure. Anyway, this research still going on because not a lot information and also research for a specific application. Again, I would say this is an opportunity, and as I said, every example I mentioned is related to the application you're going to use. So I think this has to come in package. It's not, we cannot talk individually. So process, material, application has to come together. That's the key. And if we looking at in the again, nothing actually perfect. We need to understand what is advantage and disadvantage of this. So the component of this laser melting powder-based fusion, it will be highly complex and low production rate. But feature here cannot be fabricated by other method. For example, if it's so small, you don't have any machining tools that allow you to fabricate like in the sub-micron length scale, but additive may offer that opportunity, for example. So you can customize whatever you like. For example, in implant research, metal implant research, the aim is to do the personalized implant or prosthetic, for example. So want to fit for people. And then, yeah, this is a short lead time property. Actually now is better than cast, but actually a little bit lower than wrought materials, but still improving. Actually, research need to be there So weight reduction using material structure or lattice printing, for example. And yes, this is an advantage. But at the same time, you have limitation, actually. So you limit by only some selection of material based on the understanding from welding. So weldable alloy, so sometimes printable. I prefer printable, not weldable. Or additive manufacturable rather than weldable. But anyway, a build envelope size limit. Sometimes it depends on your build chamber. If you have a smaller machine, your printed or your component will based on that, limit by that. But if you don't have a big chamber, but I will show you probably one figure later in Formnext that they use Y-based printing. Formnext is happening, I think now or just finished in Germany. So they print 3-meter component using metal printing. So it's coming now. It's even, yeah. So for example, surface roughness is still issue because especially the rotating part that you require fatigue and then creep life. So you need to come with package again, not only material fabrication, but also probably a little bit processing, how you treat the process to make the part actually usable or robust. Yeah, build microstructure requires some processing. And then there is some waste actually generated from this or unused powder. How can we recycle it? It's another challenge topic that people are trying to do, using or recycle some reused powder. And also probably at the moment, the advantage from the economic point of view is actually more expensive than traditional process for now. I mean, yeah, but we think that in the near future, this cost will be reduced a lot, and then it will outweigh the traditional process for some selected or target application. Yeah, just to emphasize some first printed part, fly on air. So this is fuel nozzle by GE. I think this is made in 2012 to 2013, and this is actually weight 20% less than, because you use 3D printing. You reduce the weight by 25% for airline is important for the energy or fuel assumption, right? And then this is actually 5 times as doable. So it's more efficient. And the goal of this is not actually print one part, but we want to reduce assembly that's talked before. So each part here, print in one go. That is the aim. And this is the first 3D printed jet engine. This is a model, smaller version, printed by, I think, Monash University in Australia. And the team is Professor Xinhua Wu. Yeah, she print this part already. So it's not a dream now, it's happening. And this process, I mean, now this is about, probably this actually, in my intention is to use this time to prepare, because next session will be probably long. And then I'll try to introduce something first. So before finishing this, I mean, I think we still have time. Do you have any question at all? I think I'm speaking too long. Any question for now before move the last part? Just to give intro for the next lecture. Do you have any question? Everything clear? Good, thank you. So as I said, and then as the program stand, you know that we talk more on the melting-based additive manufacturing, especially the powder-based fusion additive process. So as I said earlier, the powder-based fusion, we have two heat sources that we can use, whether either laser or electron beam. Laser like EOS, SLM solution, I mean in terms of manufacture. And then electron beam is, for example, free melt company from, I think, Sweden as well. And then the basic process is for LPBF, actually layer by layer. The feature actually melted using laser and solidified. The key is laser and solidify. That means there will be some laser matter interaction, and then solidification will play an important role. The advantage of this process is actually, as I said before, This is the highest resolution 3D printing metal so far, so high feature resolution with the complex internal design like cooling channel. I mean, this diagram illustrates that printing process. But these advantages, as I said before, is limited by your build chamber. So the scale limit doesn't provide solution for all components. Basically, you cannot print everything. It's about the way you select it and then, which component to print. Electron beam process actually give the similar, it's layer by layer as well, but they use electron beam. Again, this is actually from metallurgical perspective, this actually advantage for some high sensitive for oxidation material like titanium. So this will perform in near vacuum condition. So you don't need to worry much about the oxygen content, and useful for reactive material, as I said. But again, this is more expensive process than laser. But now there's some company trying to reduce the price of this match with the LPBF. Again, still the research correct from the microstructure perspective. These two processes provide different microstructure. I will have a slide to show next. So, for example, this is our application. When I say material process, and then we need to say application, what is the application of this? So they also use already in NASA is a rocket chamber here. So, I mean, different model. I don't know much about that, but just to show you, this is what has been used already. And this still, in powder-based fusion, is still some challenge. Again, when I say challenge, I want to combine with the melting-based additive manufacturing process. And these include, but not limit to, the direct energy deposition, or known as bronze powder, and the powder-based fusion, or previous called SLM, or selective laser melting. So some challenge is to control microstructure. Let's see here. This is the DED, or direct energy, and this is LPBF. You will see that this is actually from Fraunhofer video here. You will see deposit material layer by layer, and this is a thin wall section, supposed to be like to repair a turbine blade. And then you will see it will be a lot going on. I will show you in the next lecture here. And then this is the LPBF, which is laser-based additive process. This is very first publication of mine, published in Acta Materia with some experimental people. So this is the effect of layer thickness. If you choose wrongly, you will end up with the subsurface porosity like this. It's just small different, but you will get the surface roughness so different. I mean, this is actually the work started in 2013 and published in 2015 in Acta, and now it's received more than 1,000 citations. It's the most citation of my paper so far, this one. And then another challenge is actually, this is a surface porosity or cracking challenge. And if you print this one using Inconel 718, this is the raw nickel-based superalloy. Again, this is a commentary in Nature Material. They say the policy needed for these additive manufacturing to make this part in order to make from A to B, which is surface finish, look good, but this is using some surface treatment. But again, if you not worry about surface, you not worry about microstructure, but the next thing you worry is about distortion. If you use neutron tomography to scan it, and you compare with the CAD model or computer-aided design model with the real print, you can map the differences of the location. And this is the purple one is mean high distortion. That means there's some part need to be taken care of. That means future is that we want to probably doing digital twin or correcting on time, on fly. Yeah, this condition actually, you distort by this bit, you collect it, something like that, a closed loop control. Again, this is, in order to do that, we need to understand the process probably much better. So when I say now, I'm scaling down and down and down, going to the very I mean, small scale. So this is a processing science of that. So this is actually the same as previous result, and this is type 6-4. So we print it and then we test it. We try to predict the subsurface porosity in this single track printing. And then this published in Scripta Acta and then in a ComNet site. Yeah? So we know that the processing complicated, even in this length scale already. But if you go into the very detailed length scale using the X-ray imaging here, you will see that the way the metal melt is quite different from the way you introduce into the model. So that means probably in order to close the gap of this one, the science needed for additive manufacturing. That is my research area, actually. So we need to understand from this local melting condition here to making the big part that can fly on air. And this is the way we know how to melt it. That's we will know how to control microstructure and property. And that means the complicated physical phenomena can occur in this micro length scale here and give rise to defect formation, which is already proved in many applications. So AM or additive manufacturing modeling is key to gain better understanding of the process in order to control this microstructure and desired property that we want. So this is actually commonly used for nickel-based superalloy. I mean, I show an example that's happening around the world from, this is Oak Ridge National Lab, like what I showed before. X1 is a SIG-15 turbine blade USA. SpaceX also use Inconel version of that. I mean, Siemens uses for gas power generation, CM247. They claim that they can print defect-free, which is, this is non-printable actually, but we can print it at some condition. And then there is a fuel nozzle as well, GE. You'll see the part here is a little bit more complicated than the one flying 2013-14. And this is a rocket engine injector from NASA. It is all a high temperature material. So in order to summarize and then try to link to the next session, I want to say that AM, metal AM especially, is specific for application. But no, yeah, it's limited at the moment. The commercial standard, especially superalloy, is used for this, used for aerospace and energy sector. Successful adoption of this actually requires fundamental understanding, like I said previously, especially understand of the linkage of process, structure, property, relationship. And then experimental method need to is based on trial and error, and it's very expensive. So we need to get insight or provide insight into the process using computer simulation sometimes. So it's not probably, we may be able to solve something easy when we dealing with some complicated equation, which you will see in it from the next lecture. And then computational design or alloy design or material design is probably key. And then I will show you as well from today, probably today or tomorrow. And then, I mean, this is the nickel-based superalloy. You will see that they since the first inception, there's so many processes optimized for different composition. So even one class of material, and now they have more than 200-300 grade available on the market, not include the one in research. But because the aerospace and energy is so important sector, as you know now, and this is actually emerging rapidly since the prototyping in 1990s, sorry. The global market actually is actually not, probably is about right, 30 billion by 25, but actually 80-something million by 28. And this one is actually, now we're trying to think about sustainability aspect. So it's reduced manufacturing cost by 170 to about 600 billion US dollars. And then that's this total energy supply reduced from 2.58 to 9.3 kilo, that this issue here. And then carbon emission actually can be reduced up to about 525 million tons by 25. So this is a sustainability aspect that I think we need to think as well for our future environment. And then that proved that in this area, I did a little bit research in the nickel-based superalloy, and you will know that from the research up until 2020, it's about 1,000 publications. But if you talk about AM overall, we have about 17,000 publications. So metal AM is quite limited. It's about only 10 times lower than the normal additive manufacturing impact for the future. That's why I choose to do it in this area. So nickel-based superalloy, a lot has been studied by US, UK, European, Indian as well, and also in the Far East. And the experimental is based on trial and error. So we may want to do simulation. And then from my research, the simulation model of paper just coming out not too long ago, less than 20 years ago. So, but my entry into this is about 2013. So it's quite early in my area as well. So I still keep working on it. It's a lot of things, a lot of interesting to do. I can promise you something very science, yeah. And then there's a lot of big room for research. As I said, even just one class of material, restricted to this high temperature application. Again, the characteristic of the process, as I said, I talk about fabrication, talk about the characteristic of process in terms of process and material. Using modeling and experiment here is an interdisciplinary approach. So you need to understand both of them in order to successfully implement that into the technology. So for example, give you some best processing window for to avoid excessive porosity, to avoid liquation or certification cracking, excessive distortion, strainage cracking. All these are metallurgical effects that can happen during printing. But how can we take into account all this in our design or doing engineering the material, engineering the process? That is the question. So ability of additive manufacturing is based on, definitely at the moment, my argument is that based on weldability. That's why I said we need to make a clear difference. It's not similar completely. So I have some paper published in additive manufacturing telling about additive manufacturability. And then anyway, there's some specific composition design that you can achieve some target. But again, you need to capture correct characteristic of the process. It's toward the end of the slide now. The trend now, again, we said about the milestone since the first machine that commercialized in about 1986, 87. If you remember first slide, now we're talking about not only prototyping or commercial customization. We're talking in the bigger scale, larger scale for the production. But again, we expect the leap of this technology actually by not too far away from here, 2025, 2030, something like that. But the next future, we need to talk about the combination of this with digital twin, with the robotics. The combination of the human-centric kind of approach. But again, that will be something for the later matter. So, and this is the trend in additive from NASA slide. As I said, they can use thermal imaging, big component, big part, and then print without our control microstructure. Or you can actually, use this additive part for controlling the surface as well. The remaining challenge is still, I come back to this slide that I will use for the next session. It's about the interaction. It's about the interaction at the lower length scale. So I think it doesn't show very well, but this one will show the melt pool. What is the liquid metal actually doing or happening during the process? Or this slide, this is Y-arc. So you will see clearly the spark of this one, then the metal deposit on this one, how the material deposit, how the temperature distribute, and how this fluid flow will all influence of the microstructure that emerging and hence property. And this will be the topic of the talk for this course, basically. I hope this is not too scientific, but I hope this will be useful. And to summarize this one, I want to say opportunity and challenge from one of my NatureCom papers, saying that we have both technological challenge and both scientific challenge that we need to solve in order to enable this technology for the future. So this is not inclusive anyway, but there's a key challenge that people looking at. For example, in the industrial perspective, they are looking at some in-situ monitoring system like thermal imaging to correct something wrong on fry, or some NDT, which is non-destructive testing qualification. Like in the implant, you want to know where is the defect or significant porosity without any destructive method. Yeah, I mean heat treatment or pros treatment or heat thermal imaging and thermal management also important. Again, this is component manufacturer is still challenge. How to make a big part without distortion and correct microstructure. From the scientific challenge, how to make powder is also challenge. Anyway, it's so expensive now. Atomization is so expensive. How can we reduce the cost and with control quality? The smaller the size of the powder, the more expensive of the kilogram per unit volume you get. And then heat source powder interaction is actually still a challenge as a function of material as well. Something we call from the metallurgical or material side perspective, the challenge is still remain in the hierarchical microstructure, because some material has some hierarchy in the microstructure which has not been fully studied yet. There's some paper from Max Planck Institute, for example, that they're looking at very thoroughly in the steel, but not all the class of material. And again, as I said before, it's specific to the application and the material and the processing route you use. So heat transfer and probably composition change, that is another challenge that I'm trying to tackle, which is, for example, if you have some composition which is material A, but finally you're printing something material B at the end, because the nickel actually lost by few atomic percent, which change totally the phase transformation that you want, let's say, in the 19 nickel titanium. There a paper published already with University of Birmingham saying that nickel can lose up to 2 atomic percent. That change the transformation temperature, martensitic transformation temperature in the body, 37, for example. And this will be very dangerous to put this part in the patient, right? Because it doesn't work in the condition needed. Yeah, that is why we need to be careful. Some material actually prone to very vaporization, composition change. It's not it's difficult to tackle, I believe, but yeah, there's some research going on. Defect formation is still an issue. Cracking, distortion, or blah blah blah, or surface roughness. That's what we're going to talk in the next few days. And having said that, I would like, I think, probably not over too much, but sorry for probably fast presentation. Next lecture in this afternoon, we'll talk about what is the physics happening in the process and how can we model it. That is the thing. And then what is a critical unsolved problem from scientific and technological perspective that we need to look at or do research. And then probably not today, but in probably later date, I will talk more about how can we link this or characterize the processing microstructure property relationship from a material system of interest. And having said that, thank you very much for listening, and any question before we close this lecture. If not, thank you very much.
So we'll assemble back at 2 o'clock after the lunch. The lunch is arranged at the Kalam International first floor, right? And 3:30 we'll have a group photo, but don't miss. So by 3:30 during that break we'll have a group photo that is in front of the library. We have to move a bit from here. So all are available at 3:30 for the group photo. Thank you.
Thank you very much. I hope this is setting the scene.
Yes, yes.
Eagerly waiting for the next lectures, sir.
Say again?
Eagerly waiting for the next lectures.
Sure. Thank you. Yes.
I have a question.
Yes, sure.
We are printing Inconel based super alloys.
Which Inconel? Oh. Just sounds. Yes. Hello. Hello. Yes. Is that okay? Closer. Hello. Hello. Hi. Hi. Okay. Hello. Walking around. Or? Hi. How are you? Yes. Is that under any question or I talking to? Is that too fast? I think it's too round, right? Hello? Yes, I think it's about okay. I mean, this is my first time in India. Apologize if I speaking too fast. And also first time to deliver this kind of course as well. Back in Queen Mary, University of London, I'm teaching on the material processing and manufacturing. But that is the all material. It's not just metal. It's not just additive, but it's for everything. Composite process, autoclaving, or standard metal, or ceramic, sintering, or yeah. But this is the first time. Normally, yes, yeah. And then another module I'm leading is actually material for aerospace application. Again, it's more materials module. It's not only mechanistic. It's actually metallurgy or material science of the material itself. So it will focus on microstructure, phase transition, something like that. Again, may I ask you, you have any background in that, or is you basically mechanical engineer? Yes. Mechanical engineer. Right. Okay. So I think it is 2:05. So shall I? Oh, another 2 minutes. Yes, sure. So this afternoon will be more about modeling. Now, how can we model it after we know a little bit about the general aspect? I believe the first part may be useful if you are a scholar, academic, or industrialist. It's made good for grant application at the first bit. Yeah, I always want to remind myself all the time and keep update information. Like now, information for 2020 is basically not useful anymore. You need to talk about 2030, mission 2050 for some country. Yeah. Yes, sure. Yes.
Using the software, the support generated automatically. And
Yes.
can we redesign the support structure so that we can minimize the thermal stresses in the part?
The answer is yes. I think that's a lot of company trying to do, right?
Yeah.
Try to, yeah, and even these the new, I mean the manufacturer will sell you with infrared diode IR infrared imaging equipment. But again, that's probably enough to basically get to print some high quality part. But again, that's what I said to you from industrial perspective. You need to do a lot of condition for that particular material, particular component, and then finally you probably licensing it or whatsoever. So it's still R&D needs to be done. Otherwise, you have quite experienced people to operate the machine, first of all, understand the part, and then I don't believe if you do it without any modeling, it's almost impossible. But model means different for different people. I mean, that's a good question because it's open to the lecture. Probably now it's 2:08. Shall we? Or we wait another 2 minutes? Right. But do we have a group photo at 3:30? Yes, yes. Yes, sure. So after this lecture, right? Right, 3:35, yes. Let's see. So we can move some of these slides to the other day. But yeah. Yes, please. Yeah, it has been done already. Yeah. Right. Yeah. Investment casting. This is my PhD project. Same-sex 4. Yeah. Yeah. Yes. Yes, yeah. Yes. Yes. Mm. Yeah. Yes. Of course, the reason we use the investment casting because we want to remove the grain boundary, which is actually decreased about 3 times of the creep life of the materials, right? But you're talking about if you use additive. At the moment, with the powder-based fusion, I think it's probably difficult to control the thermal gradients. The way we introduce in investment casting, actually, we introduce a grain selector. So we control the kind of planar thermal gradients across the geometry we are using. And then you grow only 1 grains, right? Again, if you follow some paper from Professor Kohner from Germany, from Erlangen University in Germany, she using electron beam melting to fabricate about 5 millimeter thick single crystal. Already happened. The thing is they use scanning pattern. So to mimic the way of the spiral. So they scan like this. And then the thermal gradient actually quite planar kind of thermal gradient. And you can grow single crystal. But use electron beam melting is different process. So the thing they can do this or innovate this because they understand what's happening during the LPBF and electron beam. There are some differences which they can leverage. But if you can understand the thermal, we call thermal signature of the process, you may be able to design somehow the gradient that, similar to casting situation. And then hopefully you can grow only 1 grain. That is the dream, but it still is too expensive compared with casting because electron beam is expensive. And in order to do the, I just say mass production, is even harder. Yeah, because investment casting is still expensive. Don't get me wrong, it's very expensive because it's cast 1 by 1, right? I almost by hand, yeah, from the wax loss process until machining to get the bread, yeah. But anyway, it's still property of single crystal is a lot better than polycrystal nickel-based superalloy. Still, say again? Yeah, in the hot section. We cannot replace that at the moment. Otherwise, you have better material composition which can pitch to big aerospace company. Okay, I have this, for example, high entropy alloy which outweighs the performance of CMX Soul, which I don't think no one yet trying to, because if you're good in strength, but you will not good in oxidation. and this cannot compromise or creep resistance. So that's why still CMX4 still better choice for them. Anyway, we can talk more on that. But I think it's probably time to start the modeling section. And as I said, just to remind you again that the modeling section we're talking about is based on the powder-based fusion that I'm going to talk today. And then try to map this processing map of the metal in the wider picture. You will see that there's so many, even we call about welding or fusion, I would say fusion processes. You will see that there's number of methods that you can use. I mean, from the gas welding, resistant welding, arc welding, solid state welding, including, I mean, that I showed you before, friction welding, thermochemical welding, also another thing, which may be interesting for the recent sustainable energy kind of topic at the moment, quite hot. If you can use energy, hydrogen. But this is another matter of the corrosion or embrittlement in nickel, in titanium, basically nickel and then steel, which is a big problem. Again, that is another matter for the metallurgy. But for today, it's about the radiant energy welding, or we call beam, our melting-based process. So we're talking about either fusion welding or electron beam or laser welding. And this LPBF is classified to be in this one for the manufacturing process. Anyway, in order to do all of that, I borrow one slide from University of Oxford about the process modeling that we can simulate. If you remember, in the morning we have the ring rolling here, that we want to understand the thermal distribution and subsequent phase, which is form of microstructure. You can simulate that in the ring rolling. You also can simulate the linear friction welding, rotary friction welding that I showed you earlier today. I mean, kind of friction welding. And this simulation is based on different strain rate. In this case, strain rate and also micro to macro scale simulation. If you want to simulate the chip of the machining here, this is quite high strain rate and also low, I mean, in the micro scale because it's quite small part, as well as this one. But in the bigger or manufacturing scale, like spin forming, or this is another forming, ring rolling, this require another physics, which is actually used. I mean, in short, this is solid mechanics and plasticity, blah, blah, blah. And if you want to look at more about plastic forming here, super plastic forming for the fan blade, titanium 6-4 alloy here, is actually you need to take care of probably some time phase transformation or some kind of phase change, solid transformation here, or also when you twist this one, you may want to know about this is hot creep forming, and then there's some other specific process which actually is subject to very high value added manufacturing. All of these are the case for aerospace application, which actually driven by Rolls-Royce UTC or Rolls-Royce University Technology Center at University of Oxford in solid mechanics. So that is the thing that I want to open. This is a process simulation that ultimately we want, hopefully someone or more people, more community that working on, or we have the community called computational mechanics society, I mean World Computational Mechanics Society, that will talk more about all this simulation. But for today, we talk more about the additive manufacturing. So again, I just want to emphasize again what you just mentioned about hot section of the turbine blade. Now there is a paper talking about how to print it already. I mean, back in 2016 in the Nature Materials, it's a commentary. But I mean, the summarize of this is actually successful adoption of the additive manufacturing or digital technology here to aerospace or more niche application like biomedical. It depends on the fundamental understanding of the material processing to develop some kind of data-driven, because people talking about data-driven or optimize the design of the component without actually understand the process, how you get the microstructure or those things. So this is actually key for the future. I mean, more like physical-based machine learning or a kind of reduced order model for some particular fancy component whatsoever. So the material interaction and also processing characteristic need to be captured somewhere somehow, because you want to predict defect sometime, most of the time microstructure and hence property. So this is about this talk today. So just rerun a little bit again. So we just want to print this kind of engine. If you remember this one, I will not take too much time here, but later want to emphasize here that, I mean, if you remember this video, I just want to emphasize here that there's a lot going on in one just laser interact with the material here. So you may need to understand physics or multi-physics phenomenon in the process. You may want to understand, as I mentioned earlier, about chemistry, what is happening during this interaction. And you may need to use some sensoring or data science here to correct some data on real time. As you may know, some company already have a sensorization of the process to collect the data in the one layer. It's probably cost you about 16 gigabytes of data each layer. So it's just produce a lot of data for getting the temperature field or basically red spot for defect, for example. And that's dealing with engineering AI for sure. It's just one interaction here, material design. So this gives rise to the final product as well. Process design, as I said to you. Powder metallurgy, how you make your powder, also influence. The shape of powder influence the printability of your part at the end, like spherical or elongated powder all contribute to the final property. Physical metallurgy, definitely. What happens if it's subject to something we call intrinsic heat treatment? When you print something larger and below you intrinsically heated your below layer, and that's caused different transformation of the materials sometime as well. And solid mechanics for sure, which will stress that all these contribute to modeling of additive manufacturing. So now I want to define a little bit what is the process simulation of additive manufacturing, especially melting-based process. So when people talking about modeling, I think that means different from different people. And then what I mean, because from the multi-scale perspective, modeling means different. I mean, if you talk about particle dynamics, actually I have one model above this is actually atomization. Some company approaching me now, how can the way we atomize it to get the quality powder need to be simulated as well, because they want to know what happened and how can we get rid of oxide, or for example, or scale, whatsoever. But if I'm talking about the powder-based fusion, which is spreading the powder, some research going on in the particle dynamics, spreading, swiping process. So they want to understand the packing density of the powder. So they use discrete element calculation. Again, this is classified as the modeling of additive, but it's not what I am interested in. The second is what I'm interested in, which is we call melt pool dynamic simulation or melt pool physics simulation, which is a thermal fluid dynamics. So it has to be something dealing with, again, it's different physics on computational fluid dynamics. So if you are in aerospace engineer, mechanical engineer, you may know about computational fluid dynamics calculation a lot in aeronautics. And this, we are very first one, I think in the world, I can say that we propose to use for welding and then additive manufacturing. And that's how our paper landed in 2015 in ACTA. And then next is about what happened now. What is a hierarchical microstructure that coming out, when you subject to different thermal cycle, and then that's depend on the precipitation kinetics. What happened to that? Some of you approaching me already about Inconel 718, which is the gamma double prime strengthening material. So what the matter? We need to know this because we want to understand now non-equilibrium microstructure has happened. You will not able to get the equilibrium microstructure at the nominal gamma prime percentage that you get from the spec, from this rapid sulfication process like additive. So how this emerge from as printed is something we probably need to understand a little bit, because if we do differently in terms of cross treatment, you may precipitate out some particle wrongly or not as you want. So again, this contributes also to grain size or texture. Texture control is also another matter, so we will talk more later. And another meaning of modeling, or another scale, I would say, we talk into the scale. This one probably in the 20 micron scale. This is about 100 micron length scale. This is about 1 millimeter length scale. And if you talk about centimeter length scale on the macro scale modeling, so this is now about abacus, COMSOL, or scale level of thermomechanical response, crystal plasticity, the finite element calculation. Anyway, whatsoever, just want to mention multiple physics is a finite volume calculation. So you use different computational technique as well. Specifically, in my talk, we use the volume of fluid approach to go about it. People may use different approach, but for us, we use volume of fluid. And then someone also want to get an analytical function for this complicated process. But sometimes it's too complicated because it's dealing with different length scale. How can we actually get some way somehow to make a simple single equation that can predict everything? Again, this is equation and probably is a case-by-case basis. So another way to go for this model that I believe is not individual. This one is linked together. We want to link all this information and then going to reduce all the model. So that means you just calculate some rapid modeling tools that allow you to capture all the important feature in additive process. For example, thermal signature we call, and then sometimes I propose chemical signature as well. So you don't need to know just only thermal, but sometimes chemical signature. So from concept to material as well. So that's what I see. So before we going further, we just want to have 1 or 2 slides about the what we can do. So if you remember, I mentioned about functionally graded material. If you see this Eiffel Tower, it's actually copper at the base. And then this is the steel at the top. In between, this is a graded structure, which is almost is impossible in the traditional manufacturing process. Or you talk about multi-material, which is possible now in additive. People researching it. And this is the way, the model that I said to you previously, that's useful, thermofluid dynamics. So they want to design or find some way to functionally grade this structure rather than just joining them. That's why I'm saying this is joining just one line and there is just one interaction. But this one probably, yeah, again, if you want also collectively join together is also okay. So this have a graded zone, for example, in the 718 with steel 2324. I think this is also important in the high energy kind of application because this is more expensive than this one, and also graded zone will probably improve the property in the joining zone rather than just joining them, attach them together easily. So first is actually an example of the, I would say, example of the computational modeling in additive manufacturing. So we can use like material design algorithm to I would say ranking or screen out the composition. Let's say in this case it's nickel-based superalloy, published in Acta Materia in 2021. So we map all the I think it's more than 100 nickel-based superalloy composition, but in the dot here, in the gray dot here, is about 10 million composition, which is actually calculated. And then you can map across the important 2 factor, which is the index, actually, strainage cracking. Why strainage cracking is so concerned? And the fizzing range, again, this has to be told by metallurgy. So these two factors actually give an important for the defect formation and also the processability of the material. That's why we chose these two. Okay, I mean, there's an example of the kind of AI machine learning model that you use to screen out this material we call alloy design. So what I summarize here is that map the alloy space here with the high throughput computation, more than 10 million composition here. And we use physics based, which is, I would say, not really physics based, but empirical based on the previous understanding to estimate the printability and property. So this one is a printability, and this is a kind of defect or property. But more information can be found from this paper. We map over many criteria. We can show later. So index may include strength, creep, density, phase stability that you may find is actually useful from the previous alloy design framework that apply to some component already. So we try to apply this to additive manufacturing. And then for the material process, we try to, screen out from what we believe this is an important index. This may be informed from the lower length scale modeling that you did, for example, and then link to the index for the alloy design. Again, I just give you some example. We will dive into this kind of lecture individually in probably day 4, day 5, but this is just example. And then we have to, we can reduce some experimentation. We just select to some condition that we want, and then we engage with material supplier and user to provide us this. So after some screening of the 10 million composition, we identify the new 2 composition that we believe that optimize for additive manufacturing, as mentioned earlier. So we identify this, we call alloy by design, or ABD 900 AM, which is the performance of this is good at 900 degrees centigrade and 850. So it's basically a kind of another version of Inconel 718 approximately. So if you like, so this use a lot in Inconel 718. And then we compare with some property, ideal property, but non-printable material, which is CM247 and 939. We benchmark with this property. How can we get these 2 composition to get to that property? So again, this is something we use computational physics-based model to do that. So before we going to go to this level, and then what is the background calculation needed to allow this to happen? Because I believe everyone in this room, including me, want to do alloy by design, alloy design. So find new composition, find the genome of this. I said to one of your colleagues earlier that I forgot to use this word that are actually popular in UK now. We call material passport. What I'm going to tell you at the end, we will go to get material passport, which is contain the composition, processing, property, structure in one package. And then you go to industry, and this passport can be uploaded to another machine. Again, have to be machine sensitive as well, additive. So a specific machine model, and then you can work. And that is the ultimate goal for alloy design or metallurgy or mechanical engineer people. So that is the goal, the ultimate goal. So, I mean, I don't want to recap much about this. Just want to go to the real bulk of the result. Sorry, not result, the content. So just recap again. What does it mean by each composition? Again, I think this is a recap, but yeah, shall I start here? So what we want to know is actually the processing microstructure property relationship in AM. How can we simulate it? I think this is the key, because if you can model only melt pool, what's the point? What's the use of it? There's no use actually. So we need to know more than that, just a temperature field. Why this is so helpful? So from the material, feedstock, heat source, and interaction, we need to do something going about it. And then microstructure to understand the melt pool dimension, geometry, solidification characteristic, and then subsequent microstructure information like texture, grain size, and then mechanical property, both static and dynamics property. Static is strength, dynamics is creep or fatigue, for example. And then you see here, this is Inconel 718, which is actually non-printable material. So we map using atom probe. I think here is at University of Oxford, and then we map across the around crack area after printing is at printed condition. You will see that the stress field is actually not homogeneous inside the grain. Again, this is pose another challenge because this process introduces some kind of non-equilibrium microstructure again in this level. You see this is red zone mean hard or quite hard, and then soft and hard in one grain without any, how to say, we need to do something about it using post-treatment. But if you don't know this, how can you do it? It's not just simple plasticity problem like in forging that you can homogenize using heat treatment anymore. It's more than that. So how can we go about it? And then we're using high resolution EBSD. I mean, basically, this is a sample. We map this one, and then how can we link this up and then give some guidance or some suggestion to the probably material development people to improve it or feedback somehow. So we will want to feed this information back to the, how to say, alloy design loop, if possible. So that is the goal. So again, this is just to similar, but not the same. But this is more detailed. Like this interaction actually gives rise to different solidification and hence the structure. If you know the pathway of solidification well, yeah, you may be able to change the microstructure from columnar to equiax, which is actually preferable in terms of the strength. And this is actually has first published in 2016 in Nature by the people from USA. Again, this is a concept of incontinent use. Again, apart from this processing challenge, we also have the residual stress or solid mechanics challenge or defects after that. So that's why we have a lecture here, processing and then defect of microstructure control. So again, I think we cannot see this for some reason. I think this is a technical problem, but I apologize for that. And then I think this is similar to what I showed earlier. So how can we actually simulate this to get the structure, tell something about component here to reduce distortion? That is the key. And then that's what I call process science or processing science. And then this is, again, this is similar to the previous slide this morning. But this is something different now. So, for example, if you if you want the process more powerful, you may need to understand the process. That's the thing. So, I mean, as I said before, the selection of the process is important for different materials. Let's say this is a kind of extract characteristic, briefly, from the this review article, Progressive Material Science by Professor De Broglie in Penn State, saying that, I mean, summarize very well that if you want to have very high power, it's basically actually direct energy deposition process. And also, if you want very high production rate, if you like, is actually PBF, because you see, this one is small, but this is high. But if you want a larger build, you need to use DED. But again, this is a compromise because you won't get the resolution you want. The resolution is relatively low or medium, not very high, based on the resolution based on the characteristic of the process and the feedstock resolution. And this one contributes to roughness as well, but some application require roughness. Again, that's what I said. Process, material, and fabrication has to come together as a package. So the surface roughness for biomedical may be good for the cell growth, but may not good for the rotating part in jet engine, for example. Again, this is something, so many criterion that if you are going to be ML machine learning or AI, you may need to understand this. I think it's almost impossible. We just assume from data, and then we need to have a knowledge-informed algorithm some way somehow to screen out algorithm for process, because if this is simple engineering things that you can select it with confidence, right? And then processing, again, this requires further study whether or not it's needed or it's actually okay, or what is the process requirement for this. Again, if you understand from the interaction of the material, you may be able to tell something or guide something to the relevant engineer. So just a quick recap. I mean, this is quite a lot, as I said to you before. With different atomization from water, gas, rotary, plasma rotating electrode, this gives rise to different printing. And this is so many factors. We say is so many control. I mean, something that we need to control with different geometry of this contribute to printing is proved here already. No doubts about it. Also, if you use wire and powder, it's also different. So wire is actually deposition rate is high, melt pool is big, and also again surface volume is actually there is another problem for the oxidation resistance. Let's say if you can print something like this, but it's similar to the FDM machine that you have in polymer or plastic. As you print, you will see some kind of layer here. But that means you may need to do some treatment some way, somehow. That's why hybrid manufacturing is coming. And yeah, but anyway, later, I think this is, I recap already. His source model, I'll show example. Another important thing is scanning pattern. So, I mean, I just want to say the inference of this also published in our process parameter. You see here, this is a smooth track, but if you increase the speed a lot, this is a balling effect taking place, and this actually contribute to print quality. The scanning pattern also contribute to the final product. This is just a layer thickness, a simple process parameter that we study at the very beginning. It also contribute to the porosity level as well. It's kind of cheese here, a lot of porous. It's not, you're not gonna find the plane with this structure, I'm sure. Again, my model now will try to predict and talking about this. But in order to give you one example first, I think the process parameter control can be used to do like this. This is a melt pool. You may look like, and you see the bubble creating here. And this melt pool can be actually used to melt different material here. We call in situ alloying. So let's say, for example, you have titanium and nickel, or titanium and nitinol here. You want to mix it under the beam. It's so-called in situ alloying, that the model can give you some information about chemical signature and also defect formation. And if I look at from the top view, and you will see this is how things melt together. It's so amazing, isn't it? But this is actually using the multi-phase CFD solver to get one simulation. It's probably take 1 week to calculate this one, but it will be useful for sure. I can show you a lot of example that we use this result to compare with, for example, chemical profile measurement from EPMA or from very high resolution measurement. That's basically quite match on average. So another problem is defect. I mean, again, this is, I don't want, it's quite overview, but you will see there's a lot of defects here, or surface roughness, or lack of fusion. Yeah, in order to go about not only processing defects, that's going to capture next lecture, I think in day 3. This is what we need to solve. I'm sorry for a 20 equation here, but it's actually talking about the balance between the mass equation, fluid flow, which is the momentum. This is a Navier-Stokes that you solve for CFD. It's a mass balance. And then we use a volume of fluid approach here, and you have the surface tension as a function of temperature. I mean, this is also available in the Nature Comm paper published end of last year. So there is so many things like this term contribute to the vaporization And then this actually damp the velocity in the solid. So it's around only in the liquid. This is a numerical approach to treat that the solid part is treated as a viscous, extremely viscous liquid. So this is approximation in this kind of calculation. This is actually multi-phase solver. And then in the thermal, we can add the thermal term like laser profile, whatever fancy term you want to add, or profile. For example, there's some research talking about the change of the beam profile, which actually only limited manufacturer can do that, right? For the beam profile changing, like ring donut or ellipsoid or Gaussian or blah, blah, blah. That contribute to microstructure development. I mean, this can be done in principle. I mean, anyway, what I said here, welcome for collaboration, any of them. Or vaporization is some mystery. When I say mystery, because it's actually based on the assumption of ideal gas at the moment. That balance between at the surface of the metal and the liquid metal and the atmosphere, or the gaseous phase. And then we balance the phase there, and then we assume that this behave like ideal gas, which is not whole true in the extreme rapid solidification condition. But anyway, that is a working model at the moment. And then radiation rate and heat has been taken into account to this term. So we use volume of fluid. In terms of solute diffusion, again, you will see that we use from momentum, balance of momentum, balance of energy, or thermal. We also need to incorporate some thermodynamics as well through this solute profile. This is actually complete, almost complete version of the model you can imagine. So, for example, if you are dealing with some simple elemental powder, you may not need to concern about the interaction between different elements. But if you are looking at a multi-component system like nickel-based superalloy or tertiary system, you may need to think about how can you model it in detail, if you like, in the microstructure development. So again, this one proof itself is a multi-scale problem. So for example, if I'm dealing with nickel-based superalloy, I would treat this as a pair calculation of nickel and X. X represent all the principal element that used in nickel-based superalloy, depend on which grade you're talking about. But this is up to 15 elements. So this is quite heavy calculation anyway. So there's some solidification model that you need to use. And then you need to take care of, from this, you will need to define we call mass transfer for soluto. That means segregation profile of some certain element. Again, we can neglect this one, focus purely on this. Again, these are all the things I want to talk to you in this hour. And this is an example. I think the way we simulate it, there will be a kind of specific session on day 3 that I and my postdoc will join online, will walk you through some software that we use and how we implement it to do this high fidelity, we call high fidelity simulation. But for example, if we want to use this to actually understand the alloy dependency on the different grade of nickel-based superalloy and extract something called thermal characteristic, you will see that just one calculation, each alloy composition at a given process condition. Some of you may argue that each alloy has different process condition. It's true. But for the sake of comparison, we need to use the same across to see the effect. Why this one doesn't print well is you will see it doesn't melt well as well. That's been a lot of lack of fusion. And it's evident by this thermal cycle that CM247LC, which is non-printable material, is actually high cooling rate. And also that contributes to the subsequent big distortion happening during the printing. And that's why you will get this tear off or bend it a lot. And this is just simple calculation to use this high fidelity model to give insight into some material that you want to select to print, for example. That means things required for this material to take care of. So different alloys have different thermophysical property, everyone knows. And this thermophysical property can be calculated from the thermodynamic software like JMAT Pro, thermoclock, something like that to get, if you say you decide a new composition, for example, there's no data available in literature, you may need to calculate based upon some previous result, and that's fine. And composition dependency will give rise to the microstructure and property for sure. And that's the one application of this crazy kind of modeling things we do. And another one, we can use this to approximate roughly the porosity of the materials, actually. So we can, for example, if you actually decrease the scanning speed, the porosity will be actually decreasing. As you know, you have longer time to melt, and that means the fluid can do their job properly, not too large. If it's large, it may solidify and leave the pore behind, for example. And this is another thing, is actually just simple inclination of the melt pool can probably tell you about the microstructure already. So some of you may puzzle why this so matter, just single melt pool, why it tells so much. But I want to tell you so much that you can extract for ML or machine learning AI as well. But if you do properly, so you will see that different inclination here may suggest different grain or dendritic formation if it's dendrite or it's a planar growth or cellular growth, because the characteristic length of the length scale, the microstructure doing additive almost is mostly non-equilibrium. It will be cellular structure, not quite dendrite. It will be very small fine dendrite. We'll say to you more later. And this can be used as well to predict surface roughness, which is concerned for a number of applications. That if you want to control it, I want to do some processing, but I want to understand now this process condition may give me different surface roughness, or even we can do it because from the industrial perspective, they want to minimize the manufacturing step as many as possible, right? If the process can give your perfect surface roughness profile, it's good. So we don't need to waste more money for post-processing. That is the idea. Or even we will understand and control it if it's actually detrimental. Yes, please. I can't hear you, sorry. Yes. Yes. We do for 5, 10 layers. Again, it depends on which process route you're talking about. Yeah. LPBF, yes, we can do up to about 3, 4 layers in this length scale, because I believe you appreciate that the time taken for 1 millimeter model may be 1 week, something like that, if not less. Yeah. So it's actually quite heavy calculation. But for some important condition, important material, we can run that for field condition to understand this roughness. But especially the roughness will be used a lot in the strut structure, lattices. So the scale that we simulate is similar to the arm of that strut, which is in the micro or few hundred micron length scale. So it's quite relevant length scale. But I'm not talking about big component like 10 millimeter now, yeah, if it makes sense. Yeah. We can talk more later here. But again, when you say cracking, it's different meaning for different people as well, because what does it mean by crack? If I map over 10 by 10 millimeter here, you will see there is so crack in different level. We publish data here as well in Acta Materia. You will see at the surface, these are, I think due to scanning pattern sometime, and the internal is a macro micro cracking. Again, this we will talk in the next lecture. So we can understand some way somehow from the melt pool, and then looking at different alloy composition, and then scanning pattern, and then link to the final property to define something called manufacturability of this. So I think this is just the opening for you to see the whole picture. And this is the typical characteristic microstructure for AM, LPBF especially. So along the build direction and in the transfer direction, you get different microstructure clearly. And this structure actually, when you zoom in, is actually cellular structure. And along the build, if you zoom out a little bit, this is actually, you will see some zone like this. That's what I call solute tapping zone. And this is actually quite important. And then you will see this contributes to different microstructure locally. So you have equax and columnar mixed together. And this actually very important to understand, because if not, we may choose the wrong condition, especially if this part is just 200 millimeter thickness. And then this is important for implant, for example. But I mean, in this case, it's nickel-based superalloy, not implant. But give you some example. This will be matter. So, for example, I give some. This is just overview for modeling different length scale. You will see we can use this model to predict the heterogeneity in the powder-based fusion. I mean, nickel-based superalloy. We published this already. Sorry, in Nature Communication. I think early this year. I think 24 or end of 23. Yeah, so you will be able to predict some kind of, you see, ripple here. And this is the niobium segregation profile. Because niobium will form the lava phase, which is brittle phase, is detrimental for the structure. If this phase is formed, and that mean it's so bad. So the life of the material will be decreased significantly. So we want to understand this as well. Again, just to summarize on this part before we going deep into that, is actually we saying that the number of metallurgical manufacturing available for for fusion of different similar material. When I say this similar means for in situ alloying, for welding, or for many things. Yeah, the feedstock, how to join it, whether powder bed or direct energy. Using laser or electron beam as all matter what you need to use to know, and because you need to understand the interaction of the heat source and the feedstock, and then quality of final product depend on this combination of this factor, which cannot be compromised, I would say. And typical microstructure is very fine and textured. Certification will determine the growth rate and thermal gradient under cooling, blah blah blah, and this can be tuned by scanning pattern, and then these can be tailored as well. Static property like stress, surface condition, size orientation can be controlled, I would say. And dynamic property, again, is something more to research. But we believe with the information of defects and then surface information and the microstructure information, we can estimate that approximately. So this is the first part of the this. And then now we're going to the more understanding of the fusion welding. So this is the second part. So we going to use or understand now more on the powder-based fusion. What is the process science for that? And then research method used is actually computational fluid dynamics. And then we incorporate this into material design. And then we have to capture all physical phenomena present in the metal AM, integrate them together. Not only powder particle, which some assumption, but thermochemical fluid model as well to correctly predict the grain growth and the static or solid state transformation. And this hopefully will apply to digital material design later. And this is what it's meant by different interaction and then different physics acting on it. So we can talk a little bit more now. I think again I used too many how to say repeated slides. Sorry about that. But what I want to say here is that we have particle dynamics acting on here. Again, different set of equations. We have thermal fluid, which is all those 20 equations I show you, and we may have some solid state transformation. We may have another thermodynamics equation, a long set of that for the solid transformation. What I showed you previously, this is the solid liquid vapor transition, and this is the solid transition. This is another physics. And then you have the solid mechanics, which is dealing with crystal plasticity about the material life, like crack, fatigue prediction, for example. And again, this acting on just 100 micron length scale. Just right after this is a characteristic length scale in AM. So this is what I give some commentary article in NatureCom a few years back. Yeah, and we are going to look at this from the perspective of this one. We neglect everything, just looking purely on the formation of the melt pool, what happened. Again, I will skip the part that's not relevant now or repeat it. So we use the computational method or integrated one, and you will see, I can show you the case that we did in welding. And then we use the high-speed camera to capture the dynamics of the welding. You see how the melt pool oscillated and what happened. We try to capture using simulation, solving all those equations before, and then try to predict the resultant microstructure. And this has been validated with the high-speed camera here at a different times chart here. And back in the experiment in 2015, one of my projects, and you will see that this prediction is quite well and the condition investigated. And again, this is actually used lesser set of equation, which this is a reduced version actually from those equations. But anyway, you need to couple all this to basically solve that. So that means this is a minimum that you need to solve. There's a software company provided this kind of function as well. That's called Fold 3D, which is so expensive, probably 50 grand or 50,000 pounds a year of license, something like that. That's what I heard. Even this is academic, not industry. But we use an open source code actually. We code it up from open source software. But you just need to code all those equations if you like, yeah. So from the processing design, we're not going to say it's actually like a technology push-pull approach, because we not pull from technology. But later, for additive, we say we need to use science push approach. That means you need to push the technology from science that happened in this and is still going on here. We're not filling the gap of the science that happened in this length scale yet. So a lot of synchrotron experiment, a lot of high-speed imaging things still going on, and still have some model to do. Like in additive, you may think about it, it's just that's it. No, it has a lot of application, like you use like friction stir combined with powder bed, believe me or not, or friction stir combined with DED, or you have ultrasonic with powder bed, or that's called field-assisted additive manufacturing. Again, that's not been discussed now, but just give you example. That's mean push for the process in science, how to understand this and design a new component with the property that you want. And this is the approach. So we actually need to link all this composition to process. What is the process parameter, process condition, and then link with the structure, what you want to get. Again, this can be used as indexes or output from your model, if you like, and then to link to the property of static, or we call time-independent property and time-dependent property, like creep or fatigue, for example. So we use different tools, and that means they need to have an integration component into the modeling. It's not just standalone model can answer everything. It's impossible. So we need to work across the globe to collaborate with someone who expert in thermodynamic calculation, someone expert in crystal plasticity, because no one can do it everything on your own. You need to collaborate to get the more impact. And that is some, oh, sorry. I'm not sure, for some reason it's not working, but this is a moving of the, I think it's probably working. Yes, this is, you see, this is a DED, but I'm not sure the light is quite sharp here. You see the melt pool is actually moving. And then you see the spot here is a laser, and sometimes you will see some sputter, some melt jet coming out. And if you focus clearly, there will be some plume of the vaporization. of the vapor coming out as well. A lot of things going on in just such a small length scale. Quite interesting to me because gas liquid solid transition give rise to, for example, this is a science paper theory on sputter. Vaporization hopefully coming out from us. Only one just published in NPJ computational materials already on this. Certification, whether or not it's dendrite, I think this is still clear already. It's not dendrite, it's a cellular structure. That means the way you model the certification may be different. And what is the grain and what is the thermal response and mechanical response. So if I dig down further, I mean this one just an overview, you see from the top view. But if you see from the side view, for the sake of understanding what happened in the metal powder here, some of them are actually merged together, or coalescent together and flying away. And this is the experiment carried out in 2018 in States, in Oak Ridge National Lab, if not Argonne. I think Argonne National Lab, sorry. And this paper also published in Science as well. Summarize the interaction of this, getting the beam and then contribute to the defect formation, for example. What is happening if the argon gas flow domain here or vapor jet domain here, what the matter? So, and then we can compare this or contribute or capture this with the high-speed imaging that you may have to basically close the loop here, understand this. And to summarize the science which is actually needed to simulate this kind of thing, I think I would say all this is more about physics that needed to be simulated in the model. So I summarize into the powder dynamics. So you need to probably looking about particle arrangement, translation, vibration, rotation. So it's actually a large degree of freedom that you need to calculate. Because imagine if your domain has about 10 million powder particle, you may have 30 million variable to vary. So it's almost impossible, I would say, to calculate in such a large degree of freedom like that. I mean 6 as well, not 3. Sorry, 6. And then you have this phase transition, which is, again, it depends on mel pool here. Are you talking about grain or talking about solid state transition? It's actually this bullet point, each bullet point represents different modeling scheme that you're going to use to answer those questions. So again, for my lecture, I think I want you to get, it's not about how we model it, how we implement the code, but rather want you to get the idea how complex, how multi-scale physics actually acting in the process, which is actually quite amazing. Just one single bead that you can extract a lot of information. And in casting are different characteristics because it's just controlling the temperature is a fluid flow problem, but this one is more than that, for example. And then this length scale, this is something I'm talking about. This need to link to the, we call mesoscale full field simulation, which is you may use the different approach like representative volume element approach to link all information here to get macroscopic response for the component level calculation, for example. And this can be used to establish with the failure criteria in additive. Again, this individual bit here means probably different group around the world. So the question for the community in modeling of additive, which I'm going to chair one session next year in Italy, they call the 5th International Conference in Simulation of Additive Manufacturing. We have quite big community now, so taking care of different length scale that I'm saying here, and then how can we, the big question that how can we integrate all this information? It's not just about individual contribution, but how to link them all. In US, they have a program already existing based in, I think launched in 2018. It's called X. You may know about this program. It's called exascale simulation. That is actually to do that job actually. So anyway, whatsoever, I mean this one I also keep me talking about science or interaction, what happened, that you may need to know and understand this, the signature here actually go up and down here, contribute to so many phenomena that happen. And then once you do heat treatment, aging, or hipping, this may have different defects associated with that. But how can we actually use the model that I said to you previously to screen out some way somehow or know some condition that may be combined and give a passport to one material that you can print out successfully? Again, this is a challenge problem. Research needed. It's not just simple thermal calculation from abacus can solve all the answer that you may want to know. Like defect formation is almost impossible. So example from experiment that inspire us to do simulation is actually the process itself gives stochastic nature for us to actually curious more. So for example, if you vary powder distribution, layer thickness, or scan speed, let's say in this case, layer thickness varied, scan speed varied, here, you will get different subsurface porosity or surface roughness. Again, this has been published and received a lot of, it's almost 1,100 citations already in this field. So we use CFD as well to rationalize why it happened like this. And then we kind of know that increase the layer thickness, you increase more porosity here. And if you increase scanning speed, again, the trend is not very clear, but it seems that there is a breakout point around this. So you cannot go beyond, 4 meters a second scan speed. It's probably common in our PBF system that you can, the spec of the machine we use, they said 7 meters a second. Believe me or not, but it's not true because we use high-speed imaging to correct it, and then the maximum capacity is just about 4,400 millimeters a second, which is the machine actually wrong to say the spec. But anyway, this is the big things we discover as well from the manufacturer point of view. So they said LPBF can increase a lot, but there is a limit, which probably need to study based on different material you are using. In this case, it's optimized using titanium 6-4. But different material has different characteristics. This is from experiment, but how can we model it? This is the key. So I will walk you through quickly on the modeling. I'm so sorry to give too long background, but I think it's important to understand what happened. And this is what we do. So what is the manufacturability we want to know, and what is the key process variable that matter? This is the two equations that drive our curiosity to do the modeling. So the way we do is actually, this is all the modeling framework we done and corroborate. Mostly we done in ourselves, especially in the red dash envelope here. This is what I can do straight away on the swiping. This is simple model particle dynamics. And then you do the melting. And subsequently, you will get to predict the grain structure here. And this information is heavy enough already. Before you take into, if you use incandescent 1.8 here, you may need to predict the gamma prime, double prime, gamma double prime, and delta, distribution along the build direction, which is quite surprised that you will see wavelength is not uniform anymore. And this information should be actually inserted into the mechanical model to predict the correct property that taking place induced by the signature of the process. And this, before we doing this, you can use this modeling to inform or model inform machine learning based model. So I think it's not the way, another way around. It has to be driven from science, as I mentioned earlier. So that means from this lower length scale to high length scale. And if you've done it correctly, you may be able to capture correct information needed to actually successfully print a big component in application. So first modeling is actually particle spreading. Again, we capture everything from experiment that we have. So we use experimental or laser kind of measurement of the size measurement, and then we use MATLAB to fit the cumulative distribution function here, arrange the particle in this one, assuming that there's no rotation, everything static. Otherwise, you will be in trouble. It's too much calculation. And then you spread the powder onto the bed, and then you do again to check if the simulated arrangement here similar to the experimental, which is yes. And then after that, you may actually want to print them. So thermofluidodynamic is kick in. You will get to predict the single track here. It's complicated enough. As I said, using this kind of set of equation. Again, it may look a bit different, but actually the same physics we use. But the only difference here is actually we capture different phase transition model. Rather than using simple, but we try to explicitly calculate what happened in the interface. And after that, yes, this is the use of the model. And the model can use more than just not just for the sake of the complex equation here, but there's some usage. And this one, just to summarize why using the model to rationalize metal additive manufacturing. Again, first one is actually understand the effect of the different laser mode. You may know some manufacturer provide with different modulated or continuous laser. And this one contribute largely to the melt pool characteristic in your print. So this simulation, level of simulation, give some insight into that, first of all. So you will see here, continuous, you see the blue large zone here. This is a fishing range zone, is a machi zone. This is quite sensitive. If we can reduce this zone to be quite thin, and then the crack will be minimized, for example. Second is to understand the alloy dependency in AM. Let's say you have first material, as I said, very thin blue zone, which is a machi zone, compared with alloy number 2. You have quite large zone. This actually contributes to cracking, for example. So this is not preferable. You want something like this, for example. So this is the use of the model, if you like. But without model in this length scale, it's almost impossible to get this information. Again, this also has been shown already as an example previously. Understand different alloy composition. And then we use this as well to predict the porosity-induced surface information. So we ran the model because, let's say, if you vary just one parameter, it's complex enough already. You spread the power first time, and you spread the power second time. I strongly believe that the arrangement of powder are different. Is that correct? But that means important in additive is actually, for experimentally, computationally, it's not actually deterministic, it's stochastic. And then what we need to predict or capture is the stochastic nature of it. So what we did, we ran 5 times, we spread 5 times, and then we print single track 5 times as well at the same condition. And then we extract, for each condition, we extract the kind of distribution of the subsurface porosity, and we put it in error bar, I mean in different thickness, 20, 40, 80, and 100. And this one, if you see the circle and regular, square dot here, quite aligned with each other. So the predicted porosity level using representative distributed powder arrangement is actually give quite good predictive capability for the system investigated. Rather than using simple regular, you will overestimate or underestimate the level of porosity in the build. Yes, and then you can, this is a model, this doesn't look like experiment, but this is model. Sorry, this is experiment and this is model. So we zoom in some area in single track, you will see this also published in this paper, also quite about 400 citation as well. You will see it's captured the general characteristic of the process quite well under condition investigated. And then this is actually where, the roughness we actually test in the nickel-based superalloy, previously in the titanium 6-4, using the micro CT. Again, this is single track. This is a balling, quite rough. Again, and then subsequently you will see it's probably smoother surface, but not ideal. And another thing is actually using model that I mentioned. I mean, you may familiar with the weldability diagram. I think I didn't show you, but I show you previous lecture. So rather than just based on the empirical manner, we actually calculate using CFD to predict a range of nickel-based superalloy property. So we vary two things, which is viscosity and then conductivity. And then this actually, when I map, again, I have to say I map 100 nickel-based superalloy available in literature into this map. The blue dot represent wrought superalloy. The red dot represent cast superalloy here. You will see that there is some window that actually turn green or blue. That means more printable in terms of porosity, in terms of cooling rate, which contribute to the distortion later. Cooling rate means different as well. Cooling rate from liquid to solid or from solid to solid. That has to be clearly declared. So in this case, we have in liquid and solid, which contribute to distortion, for example. And then this is a sweet spot that we can select some property that in this window. And you know, I actually map with the printable nickel-based superalloy as well. It matches quite well with this kind of CFD-based process design approach here. So we use from fundamental CFD, we use the Reynolds number, which represent a measure of the fluid flow ability and also platelet number for the heat diffusion to actually screen out some condition. Let's say in the red spot here is not useful. We need to go to the bruise window here for better design from the process perspective that contribute to the indexes for the alloy design, for example. Like you try to control that, okay, you prefer probably thermal conduction or thermal, diffusivity of this range, for example. And then this one will then feed into this kind of processing simulation, and then we can do something like elemental additive manufacturing, which actually at this one I'm trying to extract the characteristic of the AM process. I think we published in ACTA Materia as well to look at two parameters, which is diffusivity and viscosity, and you map across the transition metal in the periodic table. And you will see that, interestingly, there's a different material, property across this one, which quite clearly different. So if we interested in a main metallic system like iron, titanium, nickel, tungsten, aluminum, and gold here, at the same process condition, you can extract characteristic of the melting very well. For you can see that for gold is actually keyhole mode, while some condition here is actually just conduction mode, but keyhole but shallower, but some is with porosity as well. That's what we did. So we can see that from the mass loss perspective, the heavier element show large mass loss, and then the metal in the 3D, 4D, 5D group, mass loss, if we normalize by the atomic weight, or we call molar loss here, is similar range, but it's more sensitive to Reynolds number, which is the fluid flow of the material here. And then you can show that there is a trend in the Reynolds number map with the mass loss here, rather than it's a bit confusing in the thermal indexes, which is platelet number here. So this information will feed into the work of the in situ alloying, because ideal world, you don't want to atomize actually the powder every time you want to create a new composition. You want to create it on on fly using laser. So this is the idea that, for example, nickel titanium, you want to mix it using laser, something like that. How well they mix together is important to know, and how actually we can compensate the composition loss, that is another matter. For example, if you know that alloy powder will lead to 0.3%, 3%, 3 atomic percent loss of nickel, you can compensate about, okay, rather than 50-50, you may choose 47-53. And then just simple kind of idea that we use, and which is true. We need to compensate a lot to get finally 50-50 in the final build to get the correct property we want, for example. So we also doing the, multi-material deposition as well in the refractory metal. And this one focusing on the application of repair. When you want to repair some kind of high temperature rocket case or nuclear application, you may use some refractory materials, like in the where is niobium, moly, tungsten, tantalum. The problem is that tungsten doesn't actually join well with the base material. So that is the inspiration why we conduct this work. And then you will see that when you fabricate, first layer is actually, the substrate is nickel. We fabricate titanium like this. Yeah, like the substrate is titanium. We have molybdenum, titanium, molybdenum is alternate layer. And what we found is that different, print strategy give rise to different mixing behavior. So for example, if you look at from the longitudinal section, and this is the ranging the liquid density, you will see tantalum is a kind of laminated structure. So it doesn't mix very well with titanium. And then for hafnium, I think it's probably mixing better. This is tungsten, which is the problem that why you get a lot of crack or lamination because from the thermofluid dynamics understanding, they say that doesn't make very well. So we need to fine-tune the condition to make this mixing happen, or using some different way to mix it. So from the longitudinal or the cross-sectional area, also say that this is quite laminated for tungsten, but it's probably better in tantalum or zirconium niobium, for example. And then once we use this one, we're talking about different length scale of modeling, which is the grain structure. So we want to feed information from the CFD to predict the grain formation. Again, this is a zigzag pattern. When you have a different scanning pattern, you will create different microstructure. Again, I will have individual bit of this. I will have a lecture to go in deep into the detail how we calculate, estimate that. And this one you will see, we can capture, if we can simulate the thermal fluid here from CFD, and then we export it into CA, which is cell automata. We can at least capture the trend, but it's not ideal. I would say better way, but more expensive calculation. So this is just a proof of concept, and this may be enough already for industry to develop some microstructure-based process design, for example. Again, there is another 2D simulation for titanium 6-4 in the microstructure length scale. So what they do, if you remember the cheese line structure, using phase view, again, this is different technique. They can predict a kind of processing map from this simulation. So this is the ideal scenario that people want to do in the modeling community, that they want to predict all these map with the microstructure and the porosity defect. So this one is actually strongly coupled. It's not being detached to each other. And next length scale is actually more on what is the use of the nanoparticle like tungsten carbide to the copper, because copper is high reflectivity material. That means this will reflect a lot of energy from the laser heat source. We need to find some material that absorb energy to basically, confine energy into the domain to melt something. Otherwise, it will get lost by copper, because the absorptivity of copper is actually about 5 or less than 5%. That means 95% loss if you do it. Let's imagine this is a challenging for modeling as well, and then simulate and then experiment how can we improve the processability of copper. So some people using a more high absorptivity material to use. For example, this is tungsten, and then they try to use tungsten to melt copper, for example. And this is another work that they can use the reinforced particle and then try to predict the microstructure if you use reinforced particle. And again, this fall into the microstructure simulation, which I will talk more separately in one single long lecture as well. And again, this is a precipitation model that I said to you. If we try to do the blade geometry like this, you see in Inconel 18, when we fabricate it, according to the thermal signature, you will get some kind of wavelength or the scatter of microstructure. At the base, there's longer time for material to respond, so you get some distribution of the precipitation at the base of material. And then that means you may get high distortion from the base as well. And that justifies why it's actually bended, during printing, blah, blah, blah. And this understanding can be used after to actually fine-tune the process condition, because once you know the initial precipitation, you may be able to use some simple mean field equation to predict what happened after the thermal cycle that you use during aging and heaping, for example. And this will contribute a lot to determine the material life. For example, as you know, we use the distribution of the gamma prime, for example, for the life of nickel-based superalloy. So if we know the profile, the size of the secondary phase, we may be able to predict the life of the component. That's why it's matter. So, but another level is actually residual stress distribution. Life is so complicated in AM, and the distribution of the stress evident by neutron diffraction in Oak Ridge National Lab is not actually symmetry anymore because of the process that I mentioned earlier. For example, some condition, bad condition that contain some porosity, your residual stress profile will be changing as a dashed line here. So asymmetry here can be captured as well using Abacus simulation. I will talk to you more in another days. And then we can use this one to decide the chemical process design for AM. Again, this is just to wrap up what we do. Actually, once we can do elemental AM, this is the kind of design space that we are talking about for a number of advanced material that we can looking at for different application here as well. That is the argument for the process science that we use for this multi-metal deposition here. So I think there is some repetition. I'm sorry about that. But I think last but not least, I think this is something I want to say, because I think I see the time is quite coming now. So the key, what I want to say for additive manufacturing is that we want to have something called process-induced microstructure, because microstructure induced by the process, and the structure inform property, because structure also influence in the property to get the kind of design space here. And then when we know property, we can actually feed back into the process what is the condition that give rise to this property. So this one is actually pushed from the science, as I said, and we call this one ICME, or Integrated Computational Material Engineering Approach. And this one will get, different microstructure, definitely different property you may expect it. And I hope that this statistic from stochastic nature of the process can give you the relationship mining for the composition process and structure, and hope this framework can allow you for material discovery. Thank you very much. I'm sorry if it's too fast, but any question, please. Yeah. So I hope this is the overview of the modeling of additive, and it's not just simple thermal model that you may think, okay, use one part of thermal model can solve everything. It's not like that. It's more than that, a lot more than that, trust me. And then a lot of science papers still coming out, a lot of nature papers still coming out for additive topic, especially to understand the very fundamental aspect of it. Because sometimes the equation I show you may not, I'm not saying it's wrong, but it's just representation of what we think it should be in the process. But if we discover new science that we should incorporate into the model, that is a plus. And again, when we study more and more, we start to see more scientific point that we need to add, or actually term, for example, in the model to improve the understanding. And I hope this gives you the overall picture of mechanistic modeling of additive manufacturing. And then we will talk more in detail for individual aspect of it in the day or two. Yeah, thank you. Any question, actually? Yes, please, yeah. Morphology of indeed. Mm. Yeah, but when yeah, because what you're not going to use the full maximum energy to melt your powder, because it will be sputter everywhere. You need to find the optimum lowest power possible that you can melt without any defect, right? And that means the morphology contribute to the defect, like lack of fusion, for example. The morphology contribute to the gas porosity, gas trap porosity formation because of that nature, and because of they have more, less surface area, if you like, if you think about engineering aspect, normal. So less surface area than spherical, because it's elongated, right? Not circularity. It's actually away from circularity, and that contribute to. You will see a lot of paper in additive manufacturing talking about effect of that. Another factor of the low quality powder is that you may introduce some gas trap porosity inside the powder, and this actually contribute to the final product defect. We already published this work as well in NatureCom on the detailed pattern of the fluid flow that make pore coarsening up to probably 0.5 millimeter, quite large pore, which is detrimental for aerospace repair, for example. So I think yes, the key things is that we're not gonna bang our powder bed with high energy to make sure that everything fully melt, because you will introduce keyhole defect. You just want to go to the boundary of the conduction and keyhole mode. That is the optimum condition where you can melt it without all minimum defect as possible. So that means all factors contribute to the defect. Yeah. But another way to go about it is actually you may design some machine learning algorithm after you understand this from experiment and model, and then find a better condition for this. Again, this is another story. Thank you. Any other question? Yes. Yeah, we have a paper on ternary system. It's a heavy calculation because if you have two phases, if you have two material binary system, you need to solve 7 phases, because liquid, solid, vapor, and then you have the gases environment as well. So that means it's a 7 phases calculation rather than 2. If it's pre-alloyed powder, you have only 2 phases. But if you have 3 or tertiary system, you will have the phases up to 10. we did it as well with titanium, zirconium, copper. But this is a new alloy for medical application. It's so heavy calculation. But again, there's some commercial software that offer you as such as 4-3D. Extremely expensive one. Yeah. And then you don't have any flexibility in tweaking anything. Yeah. We can talk more about that. I'm working, and then we submit paper on that already with the detailed microstructure. Quite interesting, that one. Yeah. Thank you. I'm so
Yeah.
understand.
So then we'll take a break. First we will go to the group photo at the opposite to the library. Anyway, I will accompany you. We'll take that group photo and we'll come here and take a snacks, and by 4:10 around we can start the next session.
It's too heavy. No, it's too fast.
The subject matter is that way.
Okay, it's that way. Right?
Yeah.
Because if you want me to go to the detailed equation, it's not.
No.
I think this is the way I also give also. Hi.
అయింది అది సార్దా మందలేదా ఇక్కడ ఓ పర్లేదు నాదైనా ఆయనకి ఇచ్చేయండి ఆయనదైతే ఆయనకి ఇచ్చేయండి నాది ఉంది నాది So, good evening. So, I am not a material scientist nor a metallurgist. I am a mechanical engineer. Yeah, it is very tough after Chenapat lecture. My talk will be something related to design aspects, nothing to do with microstructure or the modeling part. So my talk will be basically on the design considerations and guidelines in additive manufacturing. Yeah, we have enough introduction to additive manufacturing, so let us try to restrict the introduction part as crisp as possible. And here the coin word is a design. So why design is so important in additive manufacturing is the conventional design is not taken here for additive manufacturing. So we'll try to see is there any approaches, design approaches, various design approaches in additive manufacturing. So yeah, that is one of the topics which I'm going to discuss. And additive manufacturing, you have a unique capabilities, right? So one among is the topology optimization, where you can optimize the structures, you can make a lightweighted structures, and we can biomimic say the designs or the structures where you are going to mimic the biological aspects or from the nature we can inspire, the designer can inspire, but now artificial intelligence, right? So you have AI inspired designs, right? So which it can be. So one can understand these designs once it has been inspired from the nature or the biological inspiration. Obviously, it is very complex, right? So the complexity is free of cost in additive manufacturing. So then you see these topology optimized structures or bionic designs. So we'll try to see how it is getting connected to AM, of course. And AM processes, yes, the previous speaker has given enough introduction or the working principles of AM. And another advantage or unique capability of additive manufacturing is part consolidation, which we have seen one of the case study from the GE. So that is, say, LEAP engine, fuel nozzle, right? So where you can consolidate several parts in an assembly or in a sub-assembly. So but definitely if that is the case, then we need to see the guidelines or we need to know the constraints of each and every process, right? Say each process, it will have its own constraints or in terms of minimum size of the feature that you can produce out of 7 AM processes, it's not same, one to other it will vary, right? So then we'll try to see some design guidelines in part consolidation kind of philosophy. And another one is a tooling area, right? So you have, say, injection molding. So injection molding dies. So where you can make a conformal cooling channels here with additive. So we'll try to see some of the design guidelines for in tool making or in designing the conformal cooling channels. We'll try to see some of the guidelines. And of course, the polymer, which the physics behind or the interaction with the material against the energy source is of course different in polymer versus metal, right? And we have enough on the metal side. Then we'll try to see some of the design rules for polymer as well as metal. And finally, build simulation. Of course, this workshop itself is for the simulation and modeling. So then we'll try to see, there are several challenges. It's not that much easy. Then we have to appreciate the expert, like how much, say, effort you put in, right? So, and still we cannot find a proprietary software which you can, we have seen several challenges which he has been explaining through his lectures, right? So we'll try to see the challenges and the build simulation scenarios, right? So this is what my presentation goes, maybe another 1 hour or 1 hour 15 minutes. Yeah, of course, as we are migrating from industry 1 to industry 4, in fact, industry 4, 5 right now. So the transition time is very less. Now the technology is growing very fast, right? If you try to see the time scale from 1 to 2, so it may be 70 years or 80, 90 years, and similarly 2 to 3. But 3 to 4, it may be 10 years or 15 years. Even 4 to 5, it is very less, right? So then one can understand the technological the advancements or the how your technologies got evolved, right? So then you are very much aware of the technologies like autonomous systems, cloud computing, system integration, simulation, IoT, augmented reality, digital data, big data analytics, cyber security, right? And then coming to the manufacturing scenario, so undoubtedly the additive manufacturing is going to play a major role in the current industrial revolution, maybe 4 or 5, whichever you call that. But the additive is going to play a major role. Even a lot of statistics and surveys are saying that additive manufacturing is going to play a major role. If you try to see the cumulative annual growth of this manufacturing, especially additive manufacturing, it's in a huge numbers, right? So then one can understand the importance of this technology. But this is not a new technology, as we know that it has started with the name called rapid prototyping, that is during late 80s or early 90s, right? And now it may be matured to a manufacturing, that's what you may be renaming, or you may be calling that as additive manufacturing, or in a, in a more, common name, it may be a 3D printing, right? So, but the essence is same, like you start with the digital data, where you maybe CAD data, maybe 3D digitized data, right? Or it may be a CT MRI in case of medical. So your digital data is the input, and where you can say from digital data to physical component or the part or assembly. Now pin to plane, you could able to make it with the additive manufacturing, right? So yeah, and this is also the previous speaker has given very elaborately coming to the traditional manufacturing, like subtractive. You have a concern about the scrap and the complexity, the product complexity, right? So this is very simple. It's a flat geometry. You don't much worry about subtractive if this is the kind of geometry. But if you change a geometry from this to a free-form coffee cup, something like this, so then we need to see several constraints here. So right. But if you have another hand, you have additive manufacturing technology. So always you work with a 2.5D dimension always, right? With a 2 dimension with a uniform thickness. So your complexity always, you never work a 3D complexity in 3D printing or additive manufacturing. Always you work 2.5D complexity with a uniform thickness, right? So that's what, but in case of traditional manufacturing, always you may work with a 3-dimensional, so instead of that, your complexity has been reduced, or rather than always you are working with a 2.5D dimension, right? And you have other concerns, whatever we have in the subtractive. So those are eliminated here, right? But you have another challenges in additive, which we are, and formative, the same case, like for in case of say molding or say you have, we need to make a die or a mold, and then again, how do you make this die or a mold? So again, you may go to the subtractive, and then the same story will repeat. But anyway, so the additive, yeah. So then cost per part versus number of parts. Obviously, the break even, like where you can see, yeah, this is what where AM or 3D printing is not meant for mass production, but it's very good for mass customization, right? You know what you mean by a mass customization, right? So that is the buzzword in Industry 4 or even in fact Industry 5. So the mass customization, so each part is unique. Each part is different geometry, different dimension. So in that case, now I will put in this manufacturing cost versus complexity now, right? So the complexity is, say, increased in a conventional manufacturing process. Your cost is also exponentially increased. So it is a quite reverse scenario, the previous graph and this graph. So your complexity is something like, it is very less complex, right? Always you have a circular, cylindrical kind of a features, but your designer has changed this design to a bio-inspired or to a topology optimized structure, right? So means your complexity, if you see this is a 1x complex, it may be a 5x or 6x complex. So then your cost is also now, it may be a 5x or it may be a 10x if you manufacture through a conventional method, right? But your additive is a guy which always remains constant, right? So irrespective of your complexity, so your cost remains same. That's what this guy is winner here. So is it only the cost? So not only cost, if you try to see the conformal cooling channel which we are talking about, so the performance of the system, right? You have the tool life, or you have the errors here in the solidification errors in case of traditional cooling channels versus your conformal cooling channels, so where your die life has been increased, right? So all that so means not only the cost reduction in terms of additive, so it will add the value to the product or the component in terms of increasing the performance of the system, right? So in case here is the die cycle time, even also it has been reduced here, the traditional tooling versus conformal cooling channel. So your performance of the system has been increased. So that is another advantage which you are going to get out of this technology, right? So you have the cost benefit as well as the performance or the efficiency of the system has been increased once you migrate to additive manufacturing. Yeah, of course, if you want to take a decision, then obviously your additive or 3D printing, so you come whenever you have a highly complex product, right? So, but that is in a limited quantity, maybe a dozen or maybe a few dozens, but not more than that. But always you look for or apt or select this 3D printing and additive manufacturing whenever you have a highly complex product, right? And you have a medium complexity and medium quantity. Of course, CNC is the right choice. And if you have a lower complexity and at the higher quantity, right, and then investment costing, but medium complexity and higher quantity, then you can go with the injection molding, right? So typically, what is the moral of the story? 3D printing and additive manufacturing. So definitely, it is, you can justify whenever you have highly complex and relatively less number. So yeah, and these are the various steps involved in any typical additive manufacturing system. You start with the CAD model, right, and then convert as STL file, and then where you have interfacing software with the machine, then you transfer this data to that software, which is say the interface with the machine. Then you do all the slicing, the laser strategy or layer thickness or whatever process parameters. You set it here. If not, the software will automatically take some default parameters, and it will generate a machine setup or rather than the code. So that code will be sent to the machine and physically layer upon other layer. So which your part from the first layer to the last layer, it is getting fabricated, and then you unload the part, remove the part. So you have the supports and you have a loose powder in case of a powder based feedstock you are using it. So you do that, you remove the part, and now you do the post-processing. Now, you are not satisfied with the mechanical properties or microstructural thing which you want to improve it, right? So, obviously, as built versus your post-processed component. Why? Because your application demands, right? So, based on the application, even your post-processing, like it can be a heat treatment, so it can be any surface treatment or heat treatment or hipping. So you can do perform several post-processing methods, maybe the application, based on the application, and as you are not satisfied with the as-built component properties, then obviously you may go with some post-processing techniques to adopt on it, right? So this is a complete value chain. So you have a design engineer, you generate the CAD model, and then you obtain the CAD and do analyze the model, right? Means maybe you want to do some perform topology optimization, right? You want to redesign. Why? Because, yeah, it is very much needed. Then very soon we'll discuss why you want to redesign always or reimagine your designers, say, and then why you want to come out with altogether a fresh design. Why not the traditional or the conventional designs or not, say, carried to additive manufacturing? So then we need to do some sort of topology or lattice design or some sort of bio-inspired designs. So then we do that and generate the tesslated model, that is STL, or it may be AMF, 3MF, right, or OBJ. So you have a tesslated data and you generate the build model, right? So then anyway, I'm not going to touch up these process plan. Maybe during the lab sessions, maybe Uday and the Srikanth is going to talk about, like, how do you set up all these in a 3D expert software, that is with the metal AM. We are going to have a lab practice on this. And once you do that, so you generate the build model, right? And then you prepare the machine, right? So you start the machine. So you have a machine operator. So and then start the machine. So that preparation of the machine is over and manufacture the part. So whatever you have, say, virtually you have done all these parameter setting and generating the code. Now physically it is getting realized here in the machine. And even we need to check with a kind of, you have a manufacturing engineer here, so where you obtain the manufacturing part, like say where you need to, say for example, you have the recycling of the powder if it is a powder based system, right? So the manufacturing engineer will come into picture and do all that. And then you have, say, the post processing of the part, just now we have discussed. So the post processing, which also covers right from the removing the supports, enhancing the properties, just now we have discussed. It may be through hipping or annealing, or maybe you are not satisfied with the accuracy, then sometimes it may be subjected to machining, and sometimes it may be a chemical polishing and surface texturing, right? So nowadays you have even short peening, milling, grinding, sanding, polishing, abrasive blasting. You have the post-processing. Again, it depends on the application and the requirement, design requirements. So then it will be subjecting to the post-processing of the parts, right? And then you have, once you complete this, and the quality assurance. Yeah, this is either you can use a NDT evaluation or you have a mechanical properties which we need to. But the challenge here is then you have a very limited standards by ASTM or ISO standards. You can see very few. Yeah, that is what which still it is evolving technology, but hardly you can find some 50 or maybe around less than 100 standards as on date. Maybe another 100 standards may be under development by ASTM and ISO together. So then that is what the quality assurance will come into picture. And then which we have next step is to the creating a digital twin, right? So that is most important part here. Now we are talking about so then creating a digital twin, and this technology is very ready to integrate with the Industry 4 technology, right? So that is what everything is a digital driven system here. unlike your conventional manufacturing system. So you can create a digital twin, right? And then machine maintenance, of course, again depends on type of machine that you are using it, right? And then cleaning up the machine and supply the powders to the machine, so all that, and ensure safety. So this is the complete value chain of any typical additive manufacturing system, right? Yeah, and coming to the design approaches, say if you on seeing this design, one can understand this is meant for a CNC technology, a subtractive manufacturing technology. Though it is a manifold, right? So it is a manifold. So on seeing this design, one can understand this is meant for a subtractive manufacturing process. This design is meant for. Why? Because you have all these 6 phases, and everything is around that 6 phases. You have arranged your say inlet and outlet things. Means your designer might have constrained by the manufacturing say manufacturability of this design. So that is the biggest thing. If at all, if you want to manufacture without changing the design here, so you have the conventional design, so you want to just print it without changing the design, then what is going to the scenario here? We will try to see. And not always, you may be constrained by, say, you are not supposed to alter the designs in some of the situations, right? Maybe it may be a spare part, for example. So you don't have a flexibility to change the design. So in that case, just you can directly say print it. But for example, this may be a 4.6 kg weight. But now you realized, no, you have a huge bulk of mass here. So then your designer thought, no, okay, this is, and maybe it may be in aerospace or application where we need to weight is a major constraint, right? So then 4.6 kg, just simply by making the bulk into a shell, now you could able to reduce the weight, that is 1 kg, right? So means just you have changed the form here. With a form change, so you could able to reduce the weight, right? And then you have that you may call as adapt for additive, but you have one more step ahead. Design for additive means not only form, so functionality means now you can see you have changed the fluid flow directions in a different way. So where your say it has improved the fluid flow, the efficiency of the system because of your design change, and also the fitment. It's very compact now, the design which you have modified, and maybe by considering the constraints of the AM also you might have tweaked the design. That may be another story. But anyway, so you have changed all 3 F's, means that is form, fitment and functionality. So you have changed. Now you realize, so it is 0.4 kg, means if you see the original design, so now you have only 91% you have a reduction of the weight, right? And not only that, your fluid flow, the performance of the system has been improved, and it has a less space required. It's very compact design, right? So then why I'm talking all this is, so next slide will tell you the story. Okay, so the same thing like a solid block you want to manufacture. Now you try to see the economics of it, right? So what could be the manufacturing cost of this manifold? So if you, as it is, without changing the design, if you want to fabricate it on a metal AM machine, right? So metal AM machine, if you want to fabricate it, for example, so if you see the scan time, the hatch pattern, it is 191 hours. Why? Because you have a huge bulk of material here. So means it is not contributing anything towards the functionality maybe. So then unnecessarily it may be increasing your scan time, means your the machine hour rate. So if you say we are going to charge say 2,000 rupees per hour on the machine, like say if it is 191 hours into 2,000 rupees, that's what which we need to bear, and plus the material cost. The material weight is now 7.4 kg, right? Maybe you can add the material cost, and the service bureau may be quoting this much amount. We want to proceed with this design. So then you might have given the code, and that it is 316L stainless steel. Imagine that it's a titanium, so it is much expensive, right? But anyway, so then you have changed it from solid block to the shell block manifold here, the same design. Now you can see it is 36 hours. So you can see how much cost you have reduced, saved, right? So from this design to this design. And further, you have adopted, say, by considering the supports and other aspects of design, aspects of IAM. So now it is only 19 hours. So which you can see how much, in terms of material, in terms of manufacturing cost, right? So that's what, so you always, you have a design, you ensure that it is always redesigned. Why? Because in order to, say, exploit, or in order to get the maximum benefit of additive manufacturing technology. Otherwise, it may be much costly, right? So if you reproduce the same design, so we need to pay heavily, right? So one can understand the design importance here in additive. Sorry for that, something else. Yeah, so if you see, your design freedom is, so your designer is not constrained by the manufacturability, or say, again, you see these, the left side one, the left side design and the right side design. So where your designer might have, say, compromised his innovation or his design based on the manufacturability of the component, maybe targeting to subtractive manufacturing process. But if you see the right side design, so where you can have a better performance of the system as well, you have a lot of design freedom once you are using this AM, right? Yeah, and then in continuation with the, say, injection molding dies, so if you have a conventional, say, the cooling channels where always you drill a straight holes like this, but you have an additive manufacturing system. Your tool has been designed with incorporating these conformal cooling channels, and you try to see the difference between the traditional tool and the additively manufactured with the conformal cooling channel. So you can find a less errors or the defects, and also the die life has been increased. So means you are adding some value to the product. And in a summary, so your manufacturing complexity is free of cost here, right? So whether it is 1x complex or it may be a 10x complex, but your cost remains same. So your manufacturing complexity is always free. Means it may be a cylindrical object, or maybe a topology optimized or a bio-inspired design like this. So you're not going to pay any extra towards this kind of complex design. So once you migrate to additive manufacturing system, right? And the variety is free, right? So imagine that you have all these different geometries. So you try to adopt any conventional method. So we need to write at least those many programs if it is a CNC, right? But here in additive, it won't care what kind of geometry that is, right? So you can, in a single setup, so you can make all these by layer. It won't care what kind of geometry that you are printing it. That is not the case in a conventional, any traditional manufacturing system, right? So your variety is free. and no assembly is required, right? That's what like we are talking about. So the part consolidation. So you can reduce the part count in an assembly or in a sub-assembly. So you sometimes in an assembly you have a less number of parts. Your maintenance is easy, and as well, so you don't have much. You have more parts, more nuisance, but you have less number of parts and less nuisance in your assembly or in your system. And zero lead time, of course, as we know that you see the supply chain in traditional versus AM. So you need only the inventory, a digital inventory, not the physical inventory in case of a traditional manufacturing systems. So you need only the digital inventory like a designs, right? So, and then your logistics is very simple here, like not unlike your conventional manufacturing systems. And unlimited design space. Again, so your designer has come out with out of the box thinking, and then there won't be any limitation for his imagination for your designer, right? So any unlimited design space you can get it. And zero skill manufacturing. Why? Because in a conventional manufacturing process, again, we need to see a lot of things here, but it is something like a push button, but it is not applicable for the metal, but maybe some extent, but the philosophy of any AM, so you have a digital data, and then it is a kind of a push button kind of a thing, right? And you don't require much of the, say, skill in the manufacturing kind of thing, unlike your conventional manufacturing system. And this is a compact, portable, right? So you have now a desktop-based machines, which it can produce a decent size, unless you have a bigger machine and producing a smaller components in case of traditional manufacturing system. But here, your system, your machinery is very compact and less wastage byproduct. Anyway, you are adding the material and infinite shades of material. This is very important, right? So you have a multi materials, structures you can make with the additive, which otherwise conventional manufacturing methods may not support this kind of infinite shades of materials. Like you have somewhere electronic material, non-electronic material, right? So you can even print them in a single setup, right? So you have infinite shades of material here, and then you have a precise physical replication, right? So you can precisely replicate. So means you have soft copy, you have a scanner and you have a printer with you. Like you can convert soft to hard or hard to soft, vice versa. Like with a kind of 3D scanning technology, if you integrate with the 3D printing technology, right? Yeah, and then you try to see the data interface, like say like your 2D printer. So any document, PDF or any kind of a form, which is ultimately post-scripting the printer, and it is getting printed, right? And similarly, STL, of course, or even it could be 3MF or AMF. So your file or your data is come with a kind of a neutral format, something like this. And STL is basically a triangular mesh data, right? But STL is not ideal. In fact, it is not ideal, right? Why? Because it doesn't support color, it doesn't support material, it doesn't support any texture, yeah. So, but it is not ideal, but still it is going as a de facto standard. The reasons, it's the simplest form. For computationally, it is very simple. Why? Because you need to perform a slicing algorithm as to do that job. But like you can come across AMF and 3MF file formats, which it can even ASTM is trying to make it as a standard format, but still it is not happening. But maybe 3MF, some industries, yes, the 3MF is very well known nowadays. Even it could be in the form of a 3MF file format, you can send it to the machine. Yeah, if you try to see the process plan involved, you have a CAD to STL to slicing, and slice to G code means you need to fill this with contours, right? So you need to have a scan strategies to fill if it is a laser based system. So this is the typical flow. And other important thing is a part orientation, right? So that's where you see the other side of the coin. So you cannot get isotropic properties in any AM produced part, right? So that is a major challenge. But again, it will vary the level of anisotropy from one process to other process, one material to other material. Yeah, like, but your part orientation is going to play a major role here in order to match or leverage your properties versus right, your orientation. Then that is one of the design consideration or the design guidelines. And again, you may have several criterions here, maybe a build time criteria, maybe a support material minimization, or maybe accuracy means you want to reduce the chord height, right? So, or staircasing effect, maybe it may be more in one orientation, other orientation. You have you have to do a lot here in order to optimize your orientation of the part. That's going to play a major role here. And slice, of course, slice thickness, more or less, it is a uniform slicing. So all proprietary machines will support only uniform slicing method, but maybe it could be a kind of adaptive slicing, or it may be a region-wise adaptive slicing kind of algorithms, but I am not sure whether proprietary machines will support such kind of, say, varying in the layer thickness between the layers. And the other aspect is support structures, right? So again, the support structure orientation, it will go hand in hand if you have one orientation, right? So you have a different supports here altogether, right? And then supports, yeah, again, and always you cannot give a general statement that always you remove the supports, but that is not a story, right? So here in the metal, we need to give somewhere the supports in order to have a proper heat conduction in your layers within the layer, or so we cannot outrightly say that always you avoid the supports or minimize the supports. Sometimes it may even useful for reducing your warpage or reducing your residual stresses that has been built up in a particular layer, right? So yeah, so then support structure, of course, we need to optimize. Yeah, how do you do in a design that thing, right? So of course, your software will suggest some sort of optimal usage of the supports, but you have a different criterions here, right? Then which criteria the software has been adopted, we don't know, right? So what is our requirement? So again, we need to say choose a right choice of your how do you tackle this kind of a support structures while designing your AM parts, right? So then if you see the typical, you have a pre-processing of the parts, that's what which you are talking about, anything related to design or your process plan, the initial, this is a pre-processing of the parts, the conceptual idea to CAD model to the conversion to STL and diagnose the STL file. You have some errors in the file. Yeah, so you have some errors in the file, right? So unfortunately, neither your CAD software nor your AM software, which is integral part of your machine, you don't have a mechanism to check whether your STL file is healthy or not, right? But you may have some third-party softwares like Magix, maybe some other softwares, right? So then here it's very important, if you give garbage in, and you will get a garbage out, right? Whether how much healthy your STL file, that is a big question here. So okay, your file, STL file is okay, then it has been diagnosed, it has been scanned, and everything is okay, then it will be, now you set up the part orientation as we discussed, like what could be the criteria to set up your or fix your part orientation, and generating the supports as well. So then while this is very important, right? If you try to see, we need to prevent the distortion, warpage, curling. So that is going to play a major role, your supports. So then how do you do that? And support overhangs, that is the angle which you have down face, up facing, right? So in that case, like how you are going to do that? And providing the balance to part and easy removal, maybe another aspect. And slicing, as we discussed, it may be an direct slicing, uniform slicing, adaptive slicing, and so on. And generation of the tool paths, maybe again like how your laser or your the extrusion nozzle, your extruder, like your raster scanning, directional scanning, and you have a different patterns. So it is going to dictate your residual stresses also, like which we are going to see maybe upcoming days, like how you can minimize those residual stresses, right? So in order to say you can do somewhat manipulating with your scan strategies, right? So you have some angle maybe which you can not allowing your residual stresses in the same plane or same layer, so then you are trying to manipulate with your laser strategies, right? And that is what you do in a pre-processing of the part. And post-processing of the part, like as we remove the support structure and you improve the surface finish, and then improving the accuracy, aesthetics, modifying the properties, reducing the porosity, maybe hipping you can, or heat treatment, or mechanical properties you can do all that stuff in post-processing of the parts, right? And then the topology optimization. But anyway, tomorrow we are going to demonstrate N topology as a one software. So we are going to see how we can design, we can say come out with. So you try to see this the CAD systems approach, like when it was started, that is during 70s, early 70s, like we used to have a parametric modeling. That was the scenario of your CAD developers used to use. But now you have a generative design, topology optimization, lattice structures, biomimicry or bionic designs, right? So okay, your designer have a lot of say ideas, taking the inspiration from the nature or the biological aspects, or your artificial intelligence. Now it is coming in a big way, like AI generated designs. So it has given tons of, say, generated ideas. Then how do you get manufactured, right? That at the end of the day, somebody has to manufacture that, right? So you have all these the complex designs, complex geometries. So then it's a big challenge for us, even for the AM also, right? Which you can see such kind of a challenges are coming up now. And one way of doing it may be simulation. Why? Because you don't have a luxury to build and you are using a titanium is the material, right? So it's a very expensive, and the machine hour rate, as I quoted, maybe 2,000 rupees per hour. Then experimentation, but it's not always possible to do that. And right, you have a lot of scope to simulate, model, simulate your multi-physics, structured modeling is coming in a big way, right? So anyway, so this is some idea, the topology optimized and bionic designs, where you are additively manufactured AM can easily produce not extra cost. Your complexity is free of cost. That's what we have been talking about, right? So you try to see all these topology optimized structures are bionic designs, right, in the aerospace structures, right? So then it may be, you can see from Airbus, Boeing, all these structural elements, it has been, the weight reduction is the major advantage here. Why? Because more or less, which you are inspiring from the biological aspects, maybe a cell biology, maybe you may be inspired, your designer may be inspired, and reducing a lot of weight. So what is the big deal in reducing a weight? Reducing a weight is a huge fuel saving, right? So even if you could able to save 1 gram payload in aircraft, that itself a big achievement. You see the entire life of the aircraft, maybe 20-25 years. So how much fuel saving, right? That is going to happen. Yeah, and monolithic structures where you can make it integral part of your, say, your fuel injector and the thrust chamber, make it as a single, in a single setup. You can say your AM, it is an Inconel super alloy, right? Inconel 718. So how you can make use of this technology, like say here again you are taking the inspiration from a lattice-based designs here. So means you are reducing the weight one hand, and also you are improving the cooling efficiency. Means your surface area, right? It's a heat exchanger. Your surface area has been increased, and you are going to get that benefit. Means your surface area has been increased, your cooling improves, and also your weight reduction, right? So that's what like companies like GE or Pat Whitney or Rolls-Royce, right? So they are adapting this kind of technology for these kind of heat exchangers, as we already discussed. Say the surface area, right here. So your surface area is more, means your designs are inspired by the biology, right? By you are biomimicking the designs, all these heat exchangers. And nowadays you can able to even print in copper. So copper is the best conductor, as we know that. So you have the best designer in the universe, that is none other than nature, right? So where you have your designer has taken the inspiration from the nature or the biology, then you have the best material for the heat exchangers, copper. Yes, you always you can get that benefit here, right? And personalization is a big for my height and weight, my pressure points are different here, right? So, and your pressure points are different, your weight and your body dynamics is different. But your shoe has been designed not considering all these aspects. But now you have a thing here, you can personalize your shoe soles, maybe for the diabetes, for example. Yes, you can always personalize these shoe soles as for the body dynamics or as per the user's requirement, right? So, and also your 3D printed dresses, right? So where the fashion designer might have taken the inspiration from the biology or the nature, right? Yeah, and if you try to see again why it is so popular in healthcare, right? And you can biomimic you have a chest implant or you have a spinal wedge implant. So you try to see your bone structure, the anatomy of the bone. So you have outer is a harder, that's a cortical bone, and if you go inside, it is porous, right? So you have a kind of a sandwich structure here. So you have outside as a solid, and if you go inside, it's much porous, right? So none other than this technology will produce or fabricate this kind of personalized implants, which is mimicking the patient anatomy. In this case, the bone, right? It could be a joint, it could be a bone, or any organ for that matter. So which you could able to personalize. That's what companies like Anatomics, Jimmers, Steiker, right? So they are deploying this kind of additive technology heavily in their medical device manufacturing. And you have orthopedic casts, right? Again, a lightweighting. So whether it is aerospace or medical, right? So lightweighting is always required. Maybe here again, the orthopedic casts, right? And if you try to see your the kind of femoral ball here, so all the weight will come, and that's what you have a solid over there, and you have a cell growth here. So the porous there, right? So none other than additive technology can produce in a single setup. Somewhere it is solid, somewhere it is porous, and that too you can control that porosity, right? So porosity may be a defect if you see in our aspect, but you are creating intentionally a porous structure which is mimicking the anatomy of the patient or the user, right? So that's what where we need to personalize those kind of designs. You try to see the topology optimized softwares like OptiStruct or Inspire or maybe N topology. Tomorrow we are going to give an N topology a demo and tomorrow session. AM processes, yeah, as for the ASTM, these are the 7 processes as we know that, and you have a polymers. Again, in the polymers, thermosets are possible through a VAT system or a material jetting system, and thermoplastics are possible through extrusion based system, right? So like that. So you have the polymers and you have the metals. It may be a non-ferrous, or it may be a ferrous, or it may be metal or metal alloy. So all sort of things are available. And ceramics, of course, you can 3D print it. Composites, again, it may be a fiber reinforced or metal matrix, right? So you can always composites. Not only the standard engineering materials class, but even you can functional, electronic, shape memory, biology, food, even the living cells could also be the material, right? That's what a regenerative medicine is all about. Say, you cannot do it in a conventional manufacturing method like this kind of material choices. Apart from engineering materials, you have natural materials, or you have even living cells of the human being is also become a material for printing, right? Yeah, I think the previous speaker might touched up all these the feedstock form and then the principles of these AM processes, and maybe a single step polymer, how these 7 AM processes will work, right? Because running short of time, I may be skipping all this. So in the, yeah, metal, even it could be a single step like your powder bed system or a DED. Yes, you can make it in a single step. But if you talk about binder jetting may be in a 2-step process, or through a material extrusion process you can do metal printing, but that is in a 2-step process. You need to debind, and then you need to sinter, and then you will get a 100% dense metal part. It is possible not only with the powder bed, not only with the DED, you can get the metal parts in other AM processes like binder jetting, material jetting, extrusion process also, right? But not in a single step. It may be in 2 steps. Yeah, if you try to see the developments in VAT, though it started with the epoxy acrylate material, right? But nowadays you can even have a sort of ceramics also can be possible, not in a direct, maybe a 2-step process. Material jetting, yes, here you can see nanoparticle jetting from X-jet. Metal can also be jetted through a material jetting system. Binder jetting, yeah, you can even go with a metal, but as I said already, it's not a single step. Maybe you do debinding, sintering, then you will get a metal part maybe through a binder jetting. And extrusion based, yes, so even metals can also be extruded, right? Like you have a mark forge, or you have other technologies where you can even produce metal, but not in a single step, maybe 2 steps. Always sheet metal, sheet lamination process, which you have a sheets or the laminates as a feedstock, and powder bed, anyway, which our course is revolving around this powder bed modeling, simulation kind of stuff. And it may be a laser, or it may be electron beam, predominantly the energy source. And directed energy, it is predominantly for metals, right? And then you have again a wire fed, or maybe a powder blown technology, right? Again, it may be a laser, or it may be a electron beam, or even it could be an arc, or even it could be something else, maybe, right? So which it can be somewhat similar to your welding technology if you try to correlate it, maybe TIG, MIG welding. But anyway, these are some of the materials versus all the 7 AM processes. So anyway, I will leave this PPT, you can have a glance afterwards. So then you talk about the part consolidation, right? So the part consolidation. So why do you want to have this kind of fasteners actually? Is there any need for the fasteners? So if you could able to eliminate those fasteners, so maybe because of some limitation in your manufacturing process, probably you made it several parts and it might have assembled together with some sort of fasteners, right? So if you have a technology which can produce without a fasteners, something like your modular kind of a design, so which we can see only the electronic parts, like it may be a motor or it may be sensors, and rest of that casing can be all your 19 components. Now it has been made only the 4 components, right? So your part consolidation is going to happen here once you have additive manufacturing technology with you. And the same thing for here, you try to see at least 48 fasteners are there, 1, 2, 3, 4, 5 components. Why? Because you could not machine like this. Probably they might have done in 5 parts, and they might have assembled it, right, with the fasteners. But like if you have any technology which can produce in a single setup, then why you want to have the fasteners? It doesn't require any fasteners at all. Maybe the limitation in the existing manufacturing processes probably that might have taken place. Yeah, this is a well-known case study. Again, this is from GE, right? And part consolidation, if you try to see, earlier it was 20 parts, and now it is only single part. All your 20 parts, now it made it as a single component like this, right? So then at least you have some 18 nozzles in a single engine. So you have 2 engines or in a aircraft, right? So then what is the biggest deal here? So your inventory has been reduced 95% and weight reduction has happened, right? And durability, 5x times durable and 30% cost efficiency. Yeah, so you have all these advantages. That's what the aero industry looking for, this kind of technology, right? And like Boeing, so and from the GE 9X engines, and then this is the most fuel efficient engine they are quoting, and 300 parts has been consolidated. See if you take, this is somewhere some diffuser part, you try to see there are 300 components, but all the 300 components made it a single component, right? So then in this way where you can consolidate your parts. So this is another case study from GE, right? So this is a catalyst series of engine, like 1/3 engine parts of the engine. So the GE is targeting additively manufacture, 3D print it. That's what. But the biggest challenge here is qualification and the certification, right? So why? Because the at least 2 areas, that is aerospace and medical, which we need to get it certified. We need to get it qualified, right? So we should not play with the lives of the people, like where they are going to fly on aircraft, or if it is a implant which it is going to fix inside the body, right? So where we need to get it certified, get it qualified, right? And like FAA, the Federal Aviation Authority, and with ISO, the ASTM, so they are working together to accelerate this qualification process. You try to see this 2015-20. So it's a 5 years they started and they got certified, right? So and if you try to see in Indian scenario, we have a DRDO components, the SEMILAC, there is a one certification agency, right? So yeah, so then the regulator or the person who certifies these kind of components, it is getting certified. Nowadays you have some accelerated procedure to get it certified. Why? Because altogether you are changing the design. It is not a conventional design. So for the conventional design, you might have a certification from the agencies, but now altogether you are in the name of part consolidation, you are redesigning the entire assembly or each and every component in your aircraft engine, but it should be getting certified, right? So, but it is happening in a fast track manner. It's not lengthy procedure nowadays. You have a simplified design. Your supply chain logistics has been reduced because of your additive manufacturing, the philosophy which you are talking about, part consolidation and all. The assembly got much simplified, and your maintenance has been simplified, right? So you have less number of parts, your maintenance cost is less, and your running cost is less. So in that way, so it can be much economical also. And the weight savings and the efficiency, the fuel burning efficiency has been 20% has been increased, and more power even they are quoting. So which we can see all these advantages. Yeah, and then coming to the tooling, the conformal cooling channel, that's what we are talking about. Like say you have a traditional tool, traditional manufacturing methods like a drilling or like any subtractive process. If you can drill only a straight drill, right, channel. But now you have say here you can confine the flow of the fluid around the part that you are going to manufacture, right? So your design, your cooling channel is designed confining to the shape that you are looking at, the component that you are looking at. The cooling stage is the major stage in any tool design area. So 60 to 70% of the cycle time. So you can reduce cycle time here, and increasing the die life, the tool life is also increased, and your cycle time has been reduced. So you are going to get these kind of advantages if you have additively make a conformal cooling channel like this, right? Yeah, this is what we are talking about. You have, if it is a traditional tool, you have a lot of internal stresses, which we can see on the left figure, and right side figure, if you see, you have all these, the warpage or the shrinkage is minimal in case of your conformal cooling channel, right? And your distortion, shrinkages, all these is minimal. Yeah, and then most important thing here is then how you can design these flow strategies, right? So you can simulate all this. So you can have the zigzag flow, or you can have the parallel flow, or you can have a spiral. You can optimize this. So based on your tool design, so you can optimize this the flow strategies, and as well your cross section of your cooling channels, right? So your cross sectional you can try simulate with the different cross sections. You try with elliptical, oval, or you can have a ribbed one, or you can have a trapezoidal kind of cross section, right? So you can come out with the optimal cross section of your conformal cooling channel. Yeah, you see here, this is the conformal cooling channel where you have say your tool has been the cooling channel has been integral part in a single setup. You can complete this. Just you design a tool with an integral cooling channel, right? And your powder bed system, you can print powder to tool in a single setup, right? So you can do all that simulation and design your tool and then print it. And this some of the case studies. Yeah, and then which we need to see, like yeah, again we need to adapt the design for additive manufacturing guidelines here to how do you remove the support structure if you have these kind of cooling channels inside, right? So then we need to play with the support structures, right? So and then post-processing methods, then you have some powder particles which it has been stuck inside your cooling channel, right? So which we need to work on that. And then coming to the last part of my presentation, so you try to see the design guidelines for the polymer AM, right? So the biggest challenge could be anisotropy, and this anisotropy is much tedious in polymer rather than a metal printing, but the polymer printing, so you have this anisotropy kind of thing is much tedious. So one can understand the application of the part that you are going to print it, right? So then based on the application, you have moving part, or you have a load which it is falling, there may be tensile compression, right? And then we need to understand the application of that part and each and every feature. We need to identify what could be the critical feature in your design. Then we need to focus, and based on that we need to fix the orientation, right? So why? Because no way you cannot eliminate the anisotropy nature of 3D printed parts. Then the best way is you try to manipulate the parameter like orientation. You try to see how best you can make it as close as, but again considering the application, the nature of the load, and which is the critical feature in your design, right? Yeah, and then you have say a flat area, something like this. So always you try to minimize your the bulk material. Don't allow in a single layer with a bulk of masses over there, right? That is a thumb rule. Why? Because if you are allowing in a single layer, so your residual stress, you have a temperature gradient, right? So where it will go, that heat dissipation may not be happen properly, right? So in that case, the good idea is make it some inclined 10-degree inclination. So then you are distributing that into number of layers. You are not allowing such kind of say the residual stress or kind of a thing not in a single layer, and you are distributing, if you make it 10-degree angle, so you are distributing that into number of layers, not in a single layer, right? So in that way, which we need to say, we need to come out from the say a conventional mindset to the additive mindset. Why? Because we need to understand first each and every process and each material different, it behaves differently, right? Then we need to understand, and based on that your design should be modified or should be tweaked or should be redesigned. So until unless you doesn't know about these ins and outs, so you may not become a good design for additive manufacturing guy. Then ultimately we may be blaming the system, right? You have a large warpage or you have a huge say distortion in the parts. Means at least we try to understand how best we can minimize in the design stage itself. Like, can it be minimized? If at all, then how it could be done, right? So in the supports, yes, it's the biggest challenge. Supports, then you tackle with a kind of overhang angle. Like you have some thumb rule, 45-degree. You try to manipulate with those kind of say and then the area also making a lot of difference here. So then whether the support material can be given over there or not, then how do you tackle that, right? So all these which we need to understand. So then you can become a very good design for additive manufacturing guy, like which we can, otherwise you may end up with some defect in the part or some build failure may happen ultimately, or if at all, if your fabrication is succeeded, but maybe some defects in your part. Yeah, and then we need to understand the minimum size of the feature that we are going to realize. That will vary from process to process, of course, and material to material. Say you have, say, you see the thickness, it may be a 2 mm thick, the left extreme, and 4 mm, 6 mm, 8 mm, 10 mm. And if the thickness is varying, so which we can see the minimum size of the feature that you are going to realize. So that is getting reduced, right? At the moment you increase the thickness of your sample, so you may not be able to realize the smallest feature, or it may be a slot or a hole or any feature for that matter, which we need to understand the constraints of the each and every process, right? So then say you maybe designed this part, but we don't know like which machine or which material you have targeted, what kind of process. Why? Because here the challenge, all 7 processes will behave differently, right? So you have a different energy source and you have a different physics involved, right? So altogether it's a different, you cannot generalize. That is the biggest challenge here. So if you talk about conventional manufacturing process, it is not the case. But the challenge here is each technology or each process behaves differently, and within the same process, each material will behave differently. That is the challenge here, right? That's what which we need to understand. And anyway, you have some kind of always don't let any bulk masses in your design. Always you try to the chop out the material, but don't let until unless, then you should not, you need to understand the application and the other aspects also. By considering that also, just like that, you cannot say that, so my machine could not do this one, then I can change my design as I wish. No, right? So then we need to balance that also, right? So you should not compromise the functionality. In fact, you are saying that you are adding the value to the product as you are changing the design. So we need to keep in mind all this, right? So accordingly we need to do it. And then you have a salt shaker holes, like especially for the VAT system or powder bed system, right? So you have a hollow part like this if you made through a powder bed system. So then you have stuck up with the loose powder inside, and it is a vat system. So you have an entrapped liquid inside of your hollow feature of your part, right? So then we need to evacuate it, or we need to evacuate that material inside, right? So for that also we have some kind of a guidelines to be followed, right? So then yeah, that is about some polymer design aspects. And coming to metal, so I will try to give some design aspects. Maybe this conference is all about simulation, modeling. Yeah, that to metal, targeting to metal, powder bed based metal laser, with the laser it has been targeted. So I will try to give some design guidelines or some considerations which we can, and then energy density. I am assuming that everybody knows about this powder bed system probably, right? So you have an energy density that is going to play a major role here, right? So even though it is a 100-watt a laser machine, so which we have only a 100-watt laser machine, but we have successfully done titanium, we have successfully done aluminum, we have successfully done cobalt chrome, we have successfully done 17.4 pH. Then here the trickiest part is how do you play with the parameters? But it may take some longer time. You have a dual laser, or you have a say 500-watt laser. I'm talking about powder bed, not DED. But DED laser rating is different. So I'm talking about only powder bed system, right? So then you can play with the parameters, like, so you try to see the energy density. It is powered by scanning speed times hatch space times layer thickness. So you try to manipulate these parameters, like which you can, right? So anyway, the biggest challenge could be a lack of fusion pores, right? And we have an expert here. Anyway, the conference is all about. But anyway, honestly, I am learning a lot from this course. So then how do you tackle that? Maybe through your microstructure manipulation, or through the kind of tailor making your properties, right? And minimizing these defects. So you try to say balance this, you minimize these, and at the same time you are trying to improve the mechanical properties, or like, so you are going to do that, right? So but anyway, so the laser absorbability, that is going to play a major role here, right? So you have a different material, the photon absorption is different from material to material, right? So anyway, so I'm not going into the deeper aspects of that. So you have absorbed energy, scattered energy, reflected energy, so all that. Yeah, the major part here is like how you are going to say make use of your scanning strategies here, right? So not allowing the residual stresses that is it has been accumulated at a region or a layer, right? So for that reason, which you are trying to alternatively, or you are varying the laser paths with some inclination, right? Some 40 degree, 45 degree, 30 degree, something like that, right? So then, which we need to do all this. So say you manipulate these parameters in such a way that maybe residual stress, maybe any sort of thing that we are working, and then other one is unsupported angles, so like your polymer, and here also. But this is very tedious here. Why? Because polymer, it's a low melting material, but it's high melting, and that too you have, it is a powder bed, always you have a single material. You don't have a choice to introduce other composition or other material, but always your powder bed, you have only single material, right? And also if it is steel, and your support is also steel, right? And then your conduction, right, is going to play, anyway we have an expert here, like which we are going to discuss all that aspects, conduction, all that thermal thermomechanical modeling of it. So anyway, your unsupported angle is going to play a major role. If you are not following that thumb rule or that guidelines, so with supports, then you are trying to build, and ultimately you may not be succeeded in your build. And unsupported overhang also, which we need to understand what could be the typical value that you, without an overhang, you can produce. If you are trying to produce, or you are designing above that threshold value, but obviously you may not be able to realize that feature, right? And similarly, here also, which you can see 1 mm, 2 mm, yeah, it is coming properly. But if you see above 2 mm, maybe 3 mm, 4 mm, 5 mm, so you could not realize. So these kind of features. Yeah, and the effect of residual stress that we have been talking about. You come out with a different the scan strategies, maybe with hatch, mander, or maybe stripe, or maybe a chessboard. Why? Because you try to see like how your interaction of the laser with the powder, right? So then, which we can, some extent, we can manipulate, not letting these residual stress in a particular region, or you try to vary the scan strategy in such a way that we can reduce these residual stresses. And another one is uneven thickness of these features, which we can see. So you follow the thumb rule, or the unlike, or like your injection molding also, like which we have some thumb rules which we need to follow here also. Always you use a uniform thickness, but not varying thicknesses. Maybe again it will create a problem here, right? And of course the stress concentration, yes. So the stress concentration here also, which you can see, not abrupt kind of the features, like you have some filleting or something like that, which you can minimize this kind of a stress concentration of the part that has been built, right? And here also uneven thicknesses, maybe it will create a lot of residual stresses and the deformation, right? So then you try to see the uniform thickness across, and then always following a filleting of it, and then horizontal holes. So the horizontal holes, which you can see right from the 2 mm, 3, 4 mm, 6 mm, 6 mm, 8 mm. You see above the 8 mm, which you can see some teardrop kind of, even though you are trying to print it in a circular one, but it's not realized. So in that case, what is the design guideline? Maybe if it is more than 8 mm, maybe slightly you change your design, maybe to the elliptical hole, or maybe a teardrop. Anyway, you are trying to build it as a circular, and you are getting a teardrop kind of a shape, and design itself you change like a teardrop. That's what you can have, and a diamond shaped holes. And the part positioning in your build platform, right, that's going to play a major role. I'm talking about the powder bed. So you have a roller or a recoater, right? So the roller or recoater, so don't put in this orientation. You have a huge force, or like you have a huge contact area with your roller with the part, right? So then you make it some 45-degree angle like this, right? So then you can minimize such kind of problem. So like that, which we need to, and don't line up like this, right? So don't line up these parts like this. You make it alternatively. So then, which we need to follow some general guidelines for positioning these. And other thing is like sometimes you're going to get a recoater, a blade will hit your the parts, right? So then the recoater will badly damage your part, right? Which we need to take care of that. And if what could be the tallest part in your build, and all that we need to consider, right? So in order to, if you consider all that, so you may not be end up with say damaging your printer or damaging your part. Yeah, and you try to see this design constraints in AM. you are trying to make some support wall like this, and you have a different aim processes, right, from the FTM, the fuse deposition, and then stereolithography, selective laser sintering, material jetting, binder jetting, and the direct metal laser sintering. So you try to see what could be the minimum size of the wall that you can realize, right? So it is varying from process to process, obviously, right? So if you see extrusion based system, yes, you have a nozzle you have some diameter, right? But you have a the VAT system like stereolithography, you have a light, right? So their energy source is light, and you have the what could be the spot size or the light thing, or like selective laser sintering, again you have the laser, what could be the laser spot size. It's going to dictate your features like a support wall or unsupported wall or any overhang, right? And then you have embossing, engraving features and horizontal bridges and minimum size of the hole that you can realize. So it is varying from process to process, but we need to understand, without targeting a particular technology, and you are designing this, and we need to understand, say for example, if you take the minimum hole size that you can realize is 2 mm in case of extrusion based system. So if you are designing a 1.5 mm hole, obviously if you are trying to print it on extrusion based system, it won't realize, right? So then we need to understand these constraints. Each and every process will have some constraints, so which we need to understand. We need to avoid such a kind of a situation where you could not build it, or there's some build failure. So because of the reasons, maybe you may not be followed the guidelines, the design guidelines properly. And you may have other features like the moving parts. So what could be the clearance between the moving parts? So again, it is varying from process to process. And you have escape holes. Just now we have discussed some salt snaker hole, like which it maybe, then what could be the size of that escape hole, and minimum size of the feature, and pin diameter, tolerance, all these, it will be varying from one process to other process, which we need to understand, right? And you try to see universities like Purdue University, so they have come out with some kind of design for additive manufacturing matrices, like just you can scan your design, and it may be it's going to give some score. It will tell you whether what is the success rate of your part that you can print. So then there will be some score. Based on the score, you can take a call, like whether we need to design a particular feature, or you can go ahead without difficulty. So based on your score, so that is you see the matrices for that: complexity, functionality, material removal, unsupported features, thin features, stress concentration, tolerance, geometrical exactness. So they have devised a matrix by say categorizing various parameters. So once you run through your design, so it will tell you the failure rate of that particular design. And build simulation, anyway, I'm not an expert, I'm also learning. So you have a multi-physics, multi-scale modeling. So in this case, you are modeling distortion, residual stresses. Anyway, tomorrow we are going to see how we can predict this kind of a thing, and then if at all, if you do compensate it, how do you get compensated? Distortion compensation and optimizing the support structures, and minimum risk of printer damage, recoder damage, which previously also we were discussing, minimizing the number of build tryouts, and predicting the impact of post-processing like heat treatment, heaping, or support removal. This is the transport or the dissipation of your heat. So you have a huge what you call, so the thermodynamics involved, or the heat transfer, the kind of a transport mechanism here, like, so you have a heat conduction, heat radiation, right, and heat you have evaporation, and you have recoil pressure, right? So anyway, we have another expert who is expert in this area, then we'll listen his lectures maybe upcoming lectures, maybe tomorrow, day after tomorrow, exclusively on that. So you try to see the simulation softwares. Anyway, which we are going to expose you on a 3D expert software, that is 3D systems metal machine, that is powder bed system. This is a 3D expert, or ANSYS additive print, and even from Hexagon there is a Simufact additive, and Make in India. Recently I met some people from Indian Make. They're already they're about to launch commercially this kind of a simulation software for powder bed system. So you have a lot of, but still this is upcoming area, but there is a huge potential. Again, it's a gray area, right, which we can see from his talk also. There is a huge potential we need to tap, or we need to work, right? So several aspects of these simulation, modeling and simulation of this powder bed system, right? So though you have some proprietary commercial softwares, but they may say that it will work for only for their machines, but how closer that data, we don't know, right? Then how, we have other softwares also under this category. Fabrication challenges, so any part, whether you made correct or wrong, that will dictated by your standards, right? So unfortunately, you don't find much standards in this space, right? So again, try to see the standards, maybe design related standards are there, and terminology related, and fabrication, feedstock related standards from ASTM and ISO together. But it's very few. You have a very few standards, but still under development several standards. That is the biggest challenge. And if you try to see the part quality of any typical powder bed system, so it at least 200, 300 parameters, it is going to affect. Like even from the previous lecture also, we came to know that there will be a huge impact or effect on the feedstock powder, right? So which we can see the material related chemical properties or powder characteristics, metallurgical properties, rheological properties of your feedstock material, right? And then optical properties. So you have a material related challenges which we need to address. And AM machine, of course, machine which we need to some extent we discussed, maybe mechanical components, maybe gas supply, maybe inerting, and your kind of the AM system related, and part related. Of course, that is a design for AM, which you can work on it, and you try to minimize those sort of challenges with the design. But everything you cannot do a design during the process, or during the feedstock preparation, or during interaction of your say energy with the feedstock, right? And you have operator pre-processing. Yes, that is during your say slicing, during slicing, or maybe during part positioning, part orientation, setting up of and the process related, of course, process parameters, right? From the layer thickness, you have a laser power or energy density, which you are talking about. So you have those process related parameters, and of course post processing at the end. So you have the support structure removal or heat treatment, surface treatment. So it's going to affect a lot, right? So we cannot say that, and you have these many combinations and permutations, like, so then how do you detect, then how do you say tackle or targeting to a particular thing and saying that, oh yeah, I have done say without any error I have done it, right? So yeah, okay, we'll so let me summarize what we have done so far. So quickly introduce this AM and design approaches in AM, like right from the direct AM, or you have three approaches which we discussed, right? And DFAM finally, design for additive manufacturing approach. Topology optimization, bionic designs. AM processes, you have a different constraints. Each and every process will have different constraints. And part consolidation, yes, you can very well use this technology for part consolidation applications. And conformal cooling channels, yes. And you have a different ball game altogether for the polymer to metal, right? And build simulation challenges. That's what this conference, like you can concentrate much on modeling simulation aspects and how you can minimize your errors or the defects, right? And anyway, you are coming to the lab. These are some of the facilities we have. We have a DMP Flex metal AM machine. Anyway, day after tomorrow, we are going to give. And even we have a material jetting system that is from ProJet 2500 plus. And we have two FDM based machines. And then, of course, we have a desktop based polymer machines and two scanners. And the softwares, exclusively softwares for medical device design and like Mimix, Magix, Thematic, 3D Sprint, 3D Export. These are the AM softwares which we have. Yeah, that's all from my side. If you have any questions, so then if you don't have questions, then we'll call the day today, and then tomorrow 9:30 you are going to start. Okay. Yeah, 9:30. Yeah, then we'll call the day today, right? So thank you for the patient listening. Yeah.